Imagine sitting outside on a quiet night, staring up at the sky. You see stars, maybe a streak of a passing satellite, maybe the faint trail of an airplane. But what if, at that same moment, something entirely invisible is reaching your body? A signal, traveling from thousands or even millions of light years away, slips through you without you ever noticing. Our planet is constantly bathed in waves from the cosmos. Radio waves, bursts of X-rays, gravitational ripples, flashes of gamma light. You are living in the middle of an ocean of signals right now. And here's the unsettling question. If one of those signals carried a message, would we even recognize it? Before we continue, a quick note. Many of you watch our videos but haven't subscribed yet, so please subscribe to our channel Restwise and join our growing community. We'd also love to know where you're watching from and what time it is for you. It's amazing to see how connected we all are. If you enjoy relaxing with philosophy, psychology, and science while drifting into sleep, give this video a like and stay with us on the journey. Now, let's get back to the video. That idea is more disturbing than it sounds, because when we think of communication, we imagine words, sounds, music, or maybe a beam of light blinking in a pattern. But the universe does not speak in ways that are convenient for humans. Sometimes it speaks in pulses so fast our brains cannot comprehend them. Sometimes it speaks in tones so low we can only pick them up with instruments the size of football fields. And sometimes it may be speaking in a language we have not yet learned how to decode. Think about that. Right now, we might already be receiving a message, and it could be slipping past us completely unnoticed. Here is where it gets really strange. Back in the late 1960s, a young astrophysicist named Jocelyn Bell Burnell was scanning data from a new radio telescope. She noticed a repeating pulse, incredibly regular, coming from a point in the sky. At first, the team jokingly labeled it LGM for Little Green Men, because the precision was too sharp, too perfect to be natural. Later, we discovered these were pulsars, collapsed stars spinning so fast they send out beams like cosmic lighthouses. But the shock of that first detection has never gone away, because for a brief moment, humanity thought the universe was speaking directly to us. And that shows how fragile the line really is between natural signal and intelligent signal. You might be thinking, well, if it was a pulsar, then mystery solved, right? But here is the uncomfortable truth. For every signal we explain, another one pops up that makes no sense. Astronomers have found bursts that last milliseconds but shine with more energy than our entire sun produces in a year. These are called fast radio bursts. They come without warning, from random points in the sky, and most vanish forever after a single appearance. Imagine hearing a knock on your door, opening it, and finding no one there. That is the emotional equivalent of these signals. They arrive, they hit our instruments, and then they disappear like ghosts. Now let's pause and really think about what that means. Humans are pattern-seeking creatures. Our brains are wired to connect dots, to find meaning in noise. This is why we see shapes in clouds, faces in shadows, voices in static. It is a survival mechanism, so when scientists stare at cosmic data and see something repeating, something pulsing, something that does not belong, our instinct is to ask who is trying to talk to us. But here is the conflict. Most of these signals have natural explanations, exotic but still physical phenomena. Magnetars, collapsing stars, quasars feeding on black holes. Yet, there is always that sliver of uncertainty. What if one of them is not natural? What if one of them is deliberate? This tension is what makes the mystery of cosmic signals so compelling. We live at a crossroads of knowledge and ignorance. On one hand, we have the most advanced instruments in history, giant arrays spread across continents, listening day and night, orbiting telescopes tuned to every frequency of light, supercomputers scanning through endless data. On the other hand, we are still like children on a beach, picking up seashells and wondering if the ocean is trying to speak to us, and the ocean in this case is the entire universe. But let me drop something heavier on you. If an advanced civilization were truly trying to communicate, they might not send messages in ways we expect. Why would they use radio when they could use neutrinos, which pass through matter almost without resistance? Why would they use visible light when they could encode information in the structure of gravitational waves? We already know that humans can send messages in forms beyond simple sound or light. DNA, for instance, is a code. Imagine if a signal arrived in the form of a pattern embedded in cosmic rays. We would not even know what we were looking at. It would pass right through our instruments, hidden in plain sight. This is where things get almost existential, because it forces us to ask not just are we alone, but are we even capable of noticing if we are not? The truth is, recognition is harder than reception. Our ears can pick up sound, but recognition turns that sound into language. Our eyes see shapes, but recognition turns shapes into meaning. The cosmos may already be singing, but our species might not have learned the melody yet. So here we are, caught between awe and unease. Signals rain down on us constantly, many of them well understood, others stubbornly unexplained. Some are violent events in deep space, some are whispers so faint we barely catch them. And somewhere in that mix, maybe hidden in the noise, could be something that changes everything. If we ever learn to recognize it, if we ever learn to listen the right way. The universe does not owe us clarity, it only sends signals. It is up to us to decide whether those signals are just noise or something more. The first recorded wow signals 1977. It was a hot August night in 1977 when a man named Jerry Emmon was sitting in front of a massive stream of data pouring in from a radio telescope in Ohio. The telescope was part of a project called the Big Air, a machine built specifically to listen for signals from the stars. Most of the time, the data was boring. Just lines of numbers and letters representing the endless background hum of the cosmos. Static, nothing special. But then, suddenly, Jerry saw something different. A signal that stood out like a flare in the dark. He was so stunned by what he saw that he grabbed a red pen, circled the numbers, and scribbled one simple word in the margin. Wow. That single word has haunted astronomy for nearly half a century, because what Jerry circled was not just another random blip. It was a radio signal 30 times stronger than the usual background noise, lasting for 72 seconds, and it seemed to come from deep space. No satellite, no plane, no earthly interference. Just a raw, powerful transmission from the cosmos. And then, like a voice that whispers in your ear and vanishes, it was gone, never to be heard again. Think about how unnerving that is. 72 seconds of clarity, and then silence. Imagine tuning your radio and suddenly hearing a crystal clear voice call your name, not static, not noise, but unmistakable precision. You freeze, waiting for it to repeat, but it never does. That is what the wow signal feels like to scientists. A fleeting moment of possible contact, leaving behind only questions. Now here is the part that gives people chills. The wow signal came from a direction in the sky near the constellation Sagittarius. That region just happens to be packed with stars, globular clusters, and even the center of our galaxy. If you were looking for a place to send a message, that is the kind of landmark you would choose. Not random, not meaningless. It is like leaving a note at the busiest crossroads on Earth. Of course, skeptics rushed in. They always do. Some suggested it might have been a reflection from a passing satellite, though none were in the right position. Others thought maybe it was a burst from a comet releasing hydrogen gas, but later studies debunked that theory. For decades, people have tried to explain the WOW signal as natural interference, but none of the ideas stick. Nothing matches the strength, the purity, and the origin of that signal, and the fact that it never repeated only deepens the mystery. Here is where the human brain takes over. We cannot help but project ourselves into the story. We imagine someone, somewhere, sending out a powerful broadcast into the void, hoping another civilization would notice. We imagine that in 1977, for a brief minute, we actually answered that call. But then the line went dead. That possibility is what keeps the WOW signal alive in our cultural imagination. It represents the thrill of maybe. Maybe we are not alone. Maybe someone reached out. Maybe we missed our only chance. And this is where the psychology becomes fascinating. Humans crave closure. When we hear a story, we want an ending. When we hear a sound, we want the next note. The WOW signal gives us neither. It dangles in front of us like an unfinished sentence, a knock on the door that no one opens. That is why it refuses to fade away, even after nearly 50 years. Because it taps directly into our need for answers. Now, let's put ourselves in Jerry Emmons' shoes. Imagine being the one who circles that data. You know that what you are seeing is extraordinary, but you also know the scientific community demands proof. And proof requires repetition. Without another detection, you have nothing but a single moment. The WOW signal is like lightning striking in front of you. Brilliant, undeniable, but gone before you can even process it. That is both the beauty and the curse of it. And here's the part that twists the knife. In the years since 1977, astronomers have scanned that same patch of sky hundreds of times with far more advanced technology. They have listened day after day, year after year, waiting for the signal to return. Nothing. Silence. It is almost cruel, as if the universe gave us a taste and then slammed the door shut. But that silence does something powerful. It fuels imagination. It keeps us searching. The WOW signal is the reason projects like SETI continue to push forward, building bigger arrays, writing smarter algorithms, hunting through mountains of data. Because if it happened once, it could happen again. And if it happens again, we might finally have the evidence we need to say we are not alone. The WOW signal has become more than just a piece of data. It is a symbol, a reminder that the universe is full of surprises, that we do not know as much as we think we do, and that sometimes the most profound discoveries come not in long explanations, but in fleeting moments. 72 seconds in 1977 changed the way we think about listening to the stars. And whether it was a natural event we still cannot explain, or the first brush with something truly alien, it left a mark on history that will never fade. Pulsars, nature's cosmic beacons. Picture a star. Not just any star, but one that has already lived its full life, burned through its fuel, and then collapsed under its own weight. Most stars fade gently, but some end with a violent finale. The kind of finale that crushes matter into something so dense, so extreme, it bends our imagination. From that chaos, something miraculous happens. A pulsar is born, and if you were floating in space nearby, You would see beams of energy sweeping across the sky like cosmic lighthouses, spinning with unbelievable speed. These are not just stars. They are timekeepers of the universe. The first time humans noticed them, scientists could not believe what they were seeing. Jocelyn Bell Burnell, a graduate student in 1967, was analyzing data when she found a signal that repeated with astonishing precision. A pulse every 1.3 seconds, over and over, too clean to be random noise. It looked engineered, like the ticking of a clock. For a moment, she and her team wondered if it was a message from intelligent life. They even labeled it LGM for little green men. But the truth turned out to be even stranger. It was not aliens. It was physics pushed to its breaking point. Here's the shocking part. A pulsar is what remains after a massive star explodes in a supernova. The core collapses into a neutron star, a sphere only about 12 miles across, but containing more mass than our sun. That means a single teaspoon of pulsar material would weigh more than Mount Everest. Let that sink in. We are talking about matter so dense that atoms themselves are crushed, electrons and protons fused into neutrons, creating a cosmic object unlike anything on Earth. And then it spins. Some pulsars rotate once every few seconds. Others spin hundreds of times per second, faster than a kitchen blender, yet with the mass of a sun. As they spin, they shoot beams of radio waves from their magnetic poles. If Earth happens to line up with those beams, we hear a pulse every time the beam sweeps past us. That pulse is so steady, so reliable, that pulsars are more accurate than atomic clocks. Astronomers use them to test Einstein's theories, to map the galaxy, even to create navigation systems for spacecraft. In other words, nature has given us cosmic GPS beacons carved out of dead stars. But here's where it gets eerie. Imagine standing on Earth, looking up, and realizing that somewhere out there are lighthouses flashing through the void. They do not care if anyone is watching. They just spin endlessly, shining their beams, indifferent to whether a planet like ours happens to notice. It almost feels like the universe leaving breadcrumbs, as if saying, "Here I am, this is how I work." And yet, the sheer precision of those pulses still unsettles people. Because it is hard to shake that first reaction Jocelyn Bell Burnell had. This feels deliberate. Now, think about human psychology for a second. When something repeats perfectly, our brains associate it with intelligence. A rhythm, a pattern, a signal. This is why a song gets stuck in your head. This is why we knock on doors in sequences. Randomness feels chaotic. Order feels intentional. Pulsars sit right at the edge of that instinct. They are perfectly natural, yet their order is so sharp it almost tricks us into thinking they are messages. That tension is part of what makes them so fascinating. And pulsars are not all the same. Some emit in radio waves, others shine in X-rays or gamma rays. Some pulse steadily, like metronomes. Others glitch, skipping a beat like a broken record, then resuming their rhythm. Astronomers call these starquakes, sudden shifts in the crust of the neutron star. Imagine an earthquake on an object denser than anything you can conceive. The energy released is beyond comprehension. Yet we can detect it, sitting here on our tiny planet, with instruments made by human hands. One of the most astonishing uses of pulsars is the idea of a pulsar map. Back in the 1970s, when NASA sent out the Voyager probes, each probe carried a golden record, along with sounds and images of Earth. There was a diagram showing the positions of 14 pulsars, with their unique pulse frequencies etched into the record. Why? Because pulsars are universal landmarks. No matter where you are in the galaxy, if you can detect those pulsars, you can find your way back to Earth. That means, right now, 2 tiny spacecraft are drifting between the stars, carrying maps that use pulsars as the guideposts of the cosmos. It is humanity's cosmic return address. But here's the question that lingers. If we can use pulsars as beacons, could someone else do the same? If an advanced civilization wanted to send a message, what better way than to embed it in the rhythm of a pulsar? A signal hiding in plain sight, carried by the most reliable timekeepers in existence. The possibility might sound like science fiction, but remember, our ancestors once thought lightning was a divine message. What feels like pure nature to us now could one day be understood as something more layered, more intentional. Whether or not pulsars hide secrets, their reality is already profound. They are reminders that death in the universe is never just an ending. A star can explode, collapse, and still leave behind something that shapes our understanding of physics, time, and navigation. Out of destruction comes a tool that lets us glimpse the machinery of reality itself. Pulsars are proof that the cosmos recycles even its most violent events into something strangely beautiful. So when you hear about pulsars, do not just think of spinning stars. Think of beacons flashing in the dark, lighthouses built by the universe itself, silently marking the pathways of space. They are not speaking to us, not really. But in their rhythm, we find meaning. And in their constancy, we glimpse a universe that keeps time more faithfully than we ever could. Fast radio bursts, FRBs, and their puzzling origins. Imagine your phone buzzing for less than the blink of an eye. Just a fraction of a second. Most of us would ignore it, brush it off as nothing. But what if that tiny vibration carried more power than the sun releases in an entire year? That is what fast radio bursts are like. Blips in the sky so brief you would miss them if you blinked, but so powerful they defy our understanding of nature. Astronomers first discovered them only in 2007, and since then they have become one of the greatest puzzles in modern astrophysics. The discovery happened almost by accident. A scientist was reviewing old telescope data when he noticed a sudden spike, a radio pulse lasting just milliseconds. At first, people assumed it was a mistake, some kind of glitch in the system. But more and more bursts kept showing up in different datasets, and suddenly, what looked like a fluke started to look like a pattern. And then came the real shocker. These signals were not local. They were not coming from nearby stars or planets. They were originating from galaxies billions of light years away. Think about the scale of that. A single burst travels across the entire cosmos for billions of years, only to slam into our instruments for a fraction of a second. If that does not make your skin crawl, here is the kicker. In those milliseconds, it outshines every star in its home galaxy combined. Imagine hearing a knock on your door so loud it shakes the entire neighborhood, but when you open it, there is nothing there. That is the emotional punch of FRBs. Now, naturally, scientists scrambled to explain them. Some thought they might be caused by magnetars, highly magnetic neutron stars capable of unleashing monstrous flares. Others suggested they could be collisions between dense objects, like neutron stars smashing into black holes. Both explanations fit some of the data, but not all. The bursts are just too weird. Some repeat, firing off signals again and again from the same source. Others appear once and never return. That mix of consistency and unpredictability makes them maddeningly difficult to pin down. And here's where human imagination kicks in. The repeating bursts are especially suspicious. If you hear a sound once, you can chalk it up to an accident. But if it happens again, and again, and again, your brain cannot help but wonder if something is trying to communicate. Some researchers even toyed with the idea that these could be intentional signals from advanced civilizations using immense energy to beam messages across the universe. After all, if we can dream of building giant radio beacons, why could not someone else? But then the skeptics remind us of something crucial. Nature has a way of outdoing us in every department. What feels impossible or artificial often turns out to be just another extreme phenomenon we had not yet imagined. Volcanoes once looked like gods breathing fire. Lightning looked like divine punishment. FRBs might just be another reminder that the universe still has plenty of tricks up its sleeve. That does not make them any less haunting. Picture this: astronomers set up arrays of radio dishes, staring at a patch of sky for weeks. Silence, silence, silence. And then, out of nowhere, a burst hits, a millisecond of raw energy, gone before you even register it. The team scrambles, checks the data, confirms it is real. But by then, it is too late. The burst has already traveled billions of years to get here, and it will never come again. The frustration of chasing something so fleeting is almost unbearable. Yet this same frustration is what drives discovery. When scientists finally caught a repeating FRB in action, it opened the door to a whole new level of study. They could finally track it to a specific galaxy. They could watch how it behaved over time. For the first time, the mystery was not just a ghost in the data. It was a real, traceable phenomenon. And still, even with all that progress, the origin question remains unresolved. Magnetars explain some bursts, but not all. Other theories keep emerging: collapsing stars, plasma interactions, even exotic physics we do not yet understand. This is where psychology comes back into play. Humans are storytellers. We crave explanations. When we see something strange, our first instinct is to assign meaning. FRBs feel like whispers from across the universe. We want them to be messages. We want them to prove we are not alone. But sometimes, the real story is that the universe is bigger, wilder, and stranger than any story we could invent. And here is a thought that lingers. If a civilization truly wanted to announce itself, what better way than through bursts of energy so powerful they could be detected across galaxies? Energy efficient. No subtle. Not at all. But effective, absolutely. The idea refuses to die, no matter how much data points us toward natural explanations. Because in the human mind, possibility is fuel. So where does that leave us? Fast radio bursts sit in the space between knowledge and mystery. We know they exist, we know they are powerful, and we know they come from unimaginably distant places. But why they happen, and what they ultimately mean, is still unsolved. They remind us that the universe is not a finished book we are reading. It is a live performance full of sudden shocks, unanswered questions, and moments of awe so intense they leave us breathless. When you think about FRBs, do not just imagine noise. Imagine the universe snapping its fingers, just once, across billions of light years, and still managing to get our attention. That is what makes them so unsettling and so beautiful. Repeating FRBs patterns from the unknown. Imagine hearing a single knock on your door late at night. You freeze, you wait, and nothing else happens. Creepy, but you can convince yourself it was nothing. Now imagine the knock happens again the next night, and then again. Suddenly your brain shifts. This is not random. This is a pattern. That is the exact feeling astronomers had when they first discovered not just fast radio bursts, but repeating ones, signals from billions of light years away, arriving in sequences, as if something out there wanted to be noticed. For years after the first FRBs were detected, they all seemed like one-off events. Mysterious, powerful, and frustratingly unrepeatable. Scientists would catch a burst lasting a millisecond, then nothing. It was like trying to study lightning by only seeing one strike. But in 2012, everything changed. A telescope in Puerto Rico picked up a burst, and then, shockingly, the same source fired again and again. Suddenly, FRBs were not just cosmic fireworks going off randomly. At least some of them were repeating, and that changed everything. Think about the implications. A one-time burst could easily be explained by catastrophic events: stars colliding, black holes feeding, explosions that happen once and are gone forever. But a repeating burst, that means the source survived. It means whatever is making these signals is not destroyed in the process. That is unsettling because it points to something persistent, something ongoing, maybe even something organized. And then came the strangest twist. One of these repeating FRBs, named FRB 1R21102, did not just repeat randomly, it showed signs of rhythm. Astronomers tracked it and realized it fired in clusters, with bursts separated by gaps of time that were eerily consistent. A cycle. Not perfect like a clock, but structured enough to feel intentional. Suddenly, the question was no longer just what causes FRBs, but why do some of them behave like they are following rules? Now let's pause and talk about human psychology. Our brains are obsessed with patterns. We cannot ignore them. This is why we hear beats in music, why we notice rhythms in speech, why we look at the stars and connect them into constellations. Patterns make us feel like something is in control. So when scientists detect repeating cosmic signals, the urge to see intelligence behind them is almost impossible to resist. After all, when you hear a knock in a pattern, you assume someone is knocking. Of course, there are natural explanations. The leading candidate is magnetars, hyper-magnetic neutron stars that can unleash bursts over and over again. Their magnetic fields are trillions of times stronger than Earth's, and the energy they release can dwarf anything we can produce. If a magnetar is surrounded by debris from its birth, interactions with that material could generate repeating signals. That explanation fits the data. But here's the catch. Not all repeating FRBs look the same. Some repeat irregularly. Some show cycles of activity and silence. Some change their intensity in ways we cannot fully predict. Even magnetars, as wild as they are, do not explain everything. And that gap, that sliver of mystery, is what keeps people awake at night, because repeating signals feel alive. They feel purposeful. When astronomers first announced repeating FRBs, people outside the field immediately leapt to the idea of communication. If you wanted to get noticed across the universe, repeating bursts would be a smart strategy. Fire once, maybe no one's listening. Fire again, and sooner or later, someone pays attention. It is hard not to feel the weight of that possibility. But here is the sobering truth. Nature itself often looks intentional. Lightning strikes and storms create repeating patterns. Volcanoes erupt in cycles. Even earthquakes can come in sequences. What feels like communication is often just the rhythm of physics, playing out on scales we do not yet understand. Still, the mystery of repeating FRBs refuses to fade because the signals are so extreme, so unlike anything else, and so far away. Billions of light years. That means they left their home galaxy long before Earth even existed, and yet we are catching them now, in real time. Imagine that for a second. You are hearing a signal today that began its journey before humans, before dinosaurs, before this planet even formed. repeating across eons, only to be picked up by a telescope built by creatures who only recently learned to make fire. That perspective alone is almost too much to wrap your head around. And yet, astronomers are not done chasing them. They have built networks of telescopes around the world, and even in space, specifically tuned to catch FRBs. They watch for repetitions, for cycles, for any sign of regularity that might unlock the code. Some scientists dream of using repeating FRBs as tools, like lighthouses to map the large-scale structure of the universe. Others cannot help but wonder if one day, hidden inside the noise, we might decode something more. A message, a sequence, a deliberate signal. Repeating FRBs sit at the edge of what we know and what we can imagine. On one side, they are extreme natural phenomena, byproducts of stars and magnetic fields. On the other side, they are the closest thing we have to what looks like a cosmic knock on the door. And until we fully understand them, they will always live in that uncanny valley between science and imagination. So the next time you hear about repeating FRBs, do not just think of them as random bursts. Think of them as echoes from the deep past, arriving with such force they shake our instruments, insisting we pay attention. They may be natural, they may be something else entirely, but either way, they remind us of one truth. The universe is not silent. It speaks in rhythms, in patterns, in pulses that travel across eternity. The real question is not whether the signals exist. It is whether we are ready to understand them. Signals from Magnetars' extreme neutron stars. In April of 2020, astronomers staring at their instruments saw something that should not have been possible. A burst of radio waves so intense, it looked like the classic fast radio bursts that had been baffling science for more than a decade. But this one was different. It was not from some far-off galaxy billions of light-years away. It came from right here in the Milky Way. The culprit, a magnetar. Magnetars are neutron stars taken to the most terrifying extreme. If a regular neutron star is already exotic, a collapsed core the size of a city yet heavier than our sun, then a magnetar is its unhinged cousin. Their magnetic fields are so strong that if you stood halfway between Earth and the Moon, the field could still erase every credit card on Earth. It is hard to even put that in human terms. Magnetars twist and warp space in ways that break our intuition. And when they unleash energy, the results can be catastrophic. That 2020 event was the first time we caught a magnetar producing something that looked exactly like an FRB. It lasted only milliseconds, but the energy was immense. Suddenly, one of the greatest mysteries in astronomy, the source of fast radio bursts, had a concrete candidate. It did not solve everything, but it proved that magnetars are capable of producing these strange cosmic signals. And in a way, that discovery only made them scarier. Because magnetars are unpredictable. They sit dormant for years, then without warning, they erupt with bursts of X-rays, gamma rays, or radio waves. Some bursts are so strong they briefly alter Earth's atmosphere, even from tens of thousands of light-years away. Think about that. A star collapsed into a neutron sphere, exploding in a galaxy on the far side of space, can still touch this planet. It is a reminder of just how violent and connected the universe really is. What makes magnetars so unstable is their internal pressure. Their magnetic fields twist the crust of the star, straining it like a spring wound too tight. Eventually, the crust cracks. Astronomers call these events starquakes, and when a starquake happens, the release of energy is beyond anything we can create or even fully imagine. A crack in the skin of a magnetar can send out a pulse that dwarfs the combined output of every power plant on Earth. These signals are so intense they can briefly saturate our detectors, as if the universe itself shouted directly into our instruments. And here's where the human brain gets tangled. When we see something repeat, or when we hear pulses and bursts, we instinctively associate them with intelligence. Our ancestors once thought thunder was the voice of gods. Today, repeating cosmic bursts still make us ask, is this a message? But with magnetars, we have evidence that raw physics can mimic that kind of rhythm. A natural object can masquerade as something deliberate. That is humbling. It forces us to admit that not every pattern in the universe is meant for us. Yet, magnetars are still mysterious. Even though we have linked them to some FRBs, not every FRB fits the magnetar model. Some bursts are too energetic. Others are too far away to match what we think magnetars can do. Some repeat in odd cycles that defy explanation. So while magnetars give us a piece of the puzzle, they are not the whole answer. And that tension keeps the door cracked open for more exotic possibilities. From a psychological perspective, that uncertainty is irresistible. We are wired to chase mysteries that are unsolved but almost within reach. Magnetars give us just enough evidence to feel like we understand them. Then they flip the table and remind us how little we actually know. It is the cosmic equivalent of a puzzle where every time you place a piece, the picture changes. But there is something beautiful in that chaos. Magnetars are not just monsters. They are laboratories of physics. By studying their signals, we learn about matter under the most extreme pressures, about magnetic fields so powerful they reshape reality, about the limits of what nature can produce. In their eruptions, we glimpse the building blocks of the universe being stretched to their breaking point. And in their bursts, we hear echoes that remind us just how alive the cosmos really is. If you zoom out and think about it, magnetars force us to confront a simple truth. The universe does not care if its signals confuse us. It does not care if they resemble messages. They exist whether we decode them or not. The responsibility falls on us to pay attention, to sort the noise from the meaning, to recognize the difference between physics and communication. And in that process, we might discover more than just the mechanics of stars. We might discover something about ourselves, about our hunger for connection, about our need to assign purpose to everything, even to the violent spasms of dead suns. So when astronomers say a magnetar has spoken, it is not poetry, it is reality. These extreme neutron stars really do send signals across the cosmos, blasts of energy so fierce they echo through space and brush against our fragile world. Whether we call them bursts, quakes, or flares, the truth is the same. Magnetars are out there, pulsing like cosmic monsters in the dark, reminding us that the universe is louder, stranger, and far more alive than we ever dared to believe. Quasars and their intense radio emissions. The brightest objects in the universe are not stars. They are not even galaxies. They are something far stranger, something that can outshine hundreds of billions of suns combined. Astronomers call them quasars, and for decades, they were among the most baffling discoveries in astronomy. At their core lies a paradox. How can something so small in scale emit more light and radio energy than entire galaxies? The story of quasars began in the 1960s, when radio telescopes picked up incredibly strong signals from what appeared to be single points of light. At first, scientists thought they must be nearby stars producing unusual radio emissions. But when researchers measured their redshifts, the stretching of light caused by the expansion of the universe. The results were shocking. These objects were not close at all. They were billions of light years away, which meant their brightness was off the charts. The power needed to generate those emissions was almost inconceivable. Here is where the shock sinks in. The energy of a single quasar can exceed the combined light of an entire galaxy. And yet, the engine that drives this phenomenon is not a sprawling network of stars. It is a black hole, a supermassive black hole millions or even billions of times heavier than our Sun, devouring matter in a frenzy. As gas and dust spiral toward the black hole, they heat up, forming an accretion disk that blazes with unimaginable intensity. And sometimes, magnetic forces near the poles of these monsters channel streams of particles outward, creating jets that blast into space at nearly the speed of light. These jets are what produce the radio signals that first revealed quasars to us. Think about how unsettling that is. A black hole, something defined by its ability to swallow light, is paradoxically the source of the brightest beacons in the cosmos. It is like finding out the darkest abyss is also the greatest lighthouse. The signals they emit travel across billions of years, meaning some of the quasars we see today lit up before Earth even existed. We are essentially watching ancient warning flares, echoes from a time when the universe was young. And here is where our instincts play tricks on us. Strong, repeating radio emissions are exactly the kind of thing we associate with communication. When astronomers first detected quasars, the regularity of the signals was so precise that some wondered if they could be artificial. Was it possible an advanced civilization had built something so powerful it could broadcast across the universe? It was a thrilling idea, but as more evidence came in, it became clear that the culprit was nature itself, just nature on a scale beyond anything we had imagined. Still, that realization does not make quasars less fascinating. In fact, it makes them even more compelling, because they show us what happens when gravity, magnetism, and matter collide at the most extreme levels. They are cosmic engines, burning with more efficiency than anything we could ever dream of building. For comparison, nuclear fusion, the process that powers our Sun, converts about 1% of mass into energy. A quasar's accretion disk can convert up to 40%. That is the difference between a flickering candle and a blowtorch big enough to light the sky. But quasars are not just astrophysical curiosities. They are tools. By studying the light from quasars, astronomers can map the large-scale structure of the universe. The beams pass through intergalactic gas on their way to Earth, leaving subtle fingerprints that tell us about the composition of matter billions of years ago. In this way, quasars are not just signals, they are records. They carry the history of the cosmos etched into their light. Now let's talk about the psychology for a second. When humans hear the word signal, our minds leap toward intention. We want to believe someone is speaking to us. Quasars remind us that not every signal is meant to be understood that way. Some signals are simply consequences of physics. Yet, that does not make them meaningless. To us, they are still messages, not from other beings, but from the universe itself. Messages that say, this is how gravity works. This is what happens when black holes feed. This is how galaxies evolve. There is also something poetic about quasars as time machines. The radio waves and light they emit travel for billions of years before we detect them. By the time those signals reach us, the quasar itself may have already quieted down. We might be staring at the ghost of a monster that no longer exists. It is as if the universe is showing us old photographs, proof of how violent and alive it once was. And in those photographs, we find patterns, rhythms, and signals that help us piece together our place in the story. Quasars also force us to confront scale. We live our lives thinking Earth is big, that the Sun is enormous, that the galaxy itself is vast. Then we realize a single quasar can outshine them all, casually throwing off energy that dwarfs everything we know. It humbles us. It makes us small. But it also excites us, because if nature can build something this extreme, what else might still be out there? What other signals are we still too limited to detect? So when you hear the word quasar, do not just think of a distant astronomical oddity. Think of them as ancient cosmic sirens, powered by black holes, sending out radio blasts across eternity. They are reminders that the universe is not quiet, that even in its darkest corners, it roars with energy. And while these signals may not be the voices of civilizations, they are still voices, voices of gravity, of time, of creation itself. Gamma-ray bursts as cosmic alarms. In the catalog of cosmic explosions, nothing is more violent than a gamma-ray burst. These events release more energy in a few seconds than our sun will emit over its entire lifetime. They are so extreme that if one ever went off close enough to Earth, it could strip away our atmosphere and end life in an instant. Astronomers call them bursts, but they might just as well be called alarms. Sudden flashes announcing that somewhere out there, the universe has just unleashed something catastrophic. The first gamma-ray bursts were discovered in the 1960s by accident. During the Cold War, the United States launched satellites to detect secret nuclear tests. Instead, those satellites picked up mysterious flashes of gamma radiation coming from space. At first, the signals were classified, treated like a potential threat. But when the truth came out, it was even more astonishing. These bursts were not from Earth at all. They were coming from deep space, and they were unlike anything seen before. The shock was not just in their power, but in their unpredictability. Gamma-ray bursts arrive without warning. A telescope may be staring at an empty patch of sky. Then suddenly, in less than a minute, a colossal explosion fills its sensors with radiation. By the time scientists react, it is usually gone. The fleeting nature of these signals makes them some of the most frustrating and compelling mysteries in astronomy. So what causes them? The leading explanations involve the deaths of massive stars or the collisions of neutron stars. When a star much larger than our Sun collapses, its core can form a black hole. As the star falls in on itself, jets of material shoot outward at nearly the speed of light. If one of those jets happens to be pointed at Earth, we detect it as a gamma-ray burst. Alternatively, when two neutron stars spiral into each other and merge, the collision can trigger the same kind of violent emission. Both scenarios involve catastrophic destruction. Stars dying, space, time itself warping, galaxies lit up by a momentary beacon of radiation. The terrifying part is scale. A gamma-ray burst can shine so brightly that it briefly outshines everything else in the observable universe. Imagine a flashlight brighter than every star in existence, concentrated into a single blinding flash. And then, in a blink, it is over. That intensity is why scientists call them alarms. They are warnings that remind us how fragile our place in the cosmos really is. And yet, as destructive as they sound, gamma-ray bursts have a hidden beauty. They are not just explosions, they are creation events. The same processes that generate these bursts also forge heavy elements like gold and platinum. Without them, the universe would be missing some of its most essential building blocks. In other words, the same forces that could wipe out life on Earth are also responsible for creating the materials that made Earth possible in the first place. Destruction and creation locked together in the same moment. Psychologically, gamma-ray bursts push against our sense of security. Humans live with the illusion of stability. We believe the ground beneath us is solid, the sky above unchanging. Then we discover that across the universe, stars are dying so violently they send shock waves of radiation that could reach us at any time. It is unsettling because it reminds us of our vulnerability, but it is also strangely motivating. By studying these bursts, we learn not just about cosmic violence, but about the very processes that shape galaxies and give rise to planets like ours. The signals themselves are haunting. Gamma rays are invisible to the human eye, so we never see them directly. Instead, we rely on specialized satellites that orbit above Earth's atmosphere, listening for the faintest flickers. When a burst goes off, alarms literally sound in observatories, triggering telescopes across the world to swivel and capture the afterglow before it fades. In that sense, gamma-ray bursts are cosmic alarms in two ways. They are destructive warnings from nature, and they trigger literal alarms in our instruments, telling us to pay attention right now. And here's something to sit with. If a gamma-ray burst ever went off within a few thousand light-years of Earth, it could cause a mass extinction. Some scientists even speculate that bursts in the distant past may have shaped the course of evolution on our planet by wiping out species and clearing the path for new ones. We owe our very existence, in part, to the destructive beauty of these cosmic events. That is both humbling and terrifying. The mystery is far from solved. Some bursts last just milliseconds. Others go on for minutes. Some leave bright afterglows across the spectrum, others vanish almost instantly. Astronomers classify them into long and short bursts, but within those categories, the diversity is staggering. Each new detection feels like a fresh puzzle, another reminder that the universe is still hiding secrets in its most violent corners. So when we talk about gamma-ray bursts, we are not just talking about explosions. We are talking about alarms, signals that cut across space and time to remind us how fragile and extraordinary existence really is. They are destructive, yes, but they are also creative. They are terrifying, but they are also illuminating. In a universe that often feels silent, gamma-ray bursts are the thunderclaps, sudden and overwhelming, demanding that we listen. The cosmic microwave background, a signal from the beginning of time. In the late 1960s, two radio engineers working in New Jersey were trying to fix a problem with their giant antenna. No matter what they did, no matter how carefully they cleaned or adjusted the equipment, they kept picking up a strange background hiss. They even climbed into the horn-shaped receiver and shoveled out what they politely described as pigeon droppings, thinking maybe birds were the culprit. But the noise remained. What they had stumbled onto was not interference at all. It was the oldest signal ever detected, a faint glow from the birth of the universe itself. That discovery became known as the cosmic microwave background. It is not a local signal. It is not from stars or galaxies or even black holes. It is the afterglow of the Big Bang, the leftover radiation that has been traveling through space for nearly 14 billion years. Every direction you point a sensitive radio receiver, that faint static is there. It is everywhere because it comes from everywhere. And here is the staggering part. When we talk about this signal, We are not just describing a distant echo. We are looking back in time to an era when the universe was only about 380,000 years old. Back then, the cosmos was a hot soup of particles so dense that light could not travel freely. But as it cooled, atoms began to form, and suddenly the fog lifted. For the first time, photons could move unhindered. Those first rays of light have been traveling ever since, stretched into microwaves by the expansion of space, and today they wash over us constantly. The shock of this discovery cannot be overstated. Before it was found, the Big Bang was just one theory among many. Some scientists believed the universe had always existed in a steady state, endlessly renewing itself. The cosmic microwave background ended that debate. It was physical proof that the universe had a beginning, that it expanded from something unimaginably hot and dense, and that its story is written in the radiation still whispering across the sky. And here is where the human mind struggles. When you turn an old television to static and see the random snow on the screen, about 1% of that noise is this ancient signal. That means if you have ever stared at TV static, you have literally seen the echo of the birth of the universe. That simple fact collapses the distance between ordinary human life and the most profound cosmic event imaginable. But the cosmic microwave background is not uniform. When scientists mapped it with satellites like QOB, WMAP, and later Planck, they found subtle variations, tiny fluctuations in temperature and density. Those fluctuations are the seeds of everything. They are the reason galaxies formed, the reason stars clustered together, the reason Earth even exists. Without those slight differences, the universe would be a smooth, featureless soup. Instead, the background shows us a cosmic fingerprint, proof that structure and life itself were encoded into the universe from its very beginning. Think about what that means. Every mountain, every planet, every living creature traces back to small ripples in a glowing field nearly 14 billion years old. The static those engineers heard in New Jersey was not just noise. It was the foundation of reality, humming in the background of everything we know. And yet, the cosmic microwave background does more than confirm the Big Bang. It also raises questions that we are still wrestling with. The variations we see are incredibly precise, suggesting that the early universe was almost unnaturally uniform. Some scientists explain this with the idea of cosmic inflation, a brief moment of faster than light expansion in the universe's infancy that smoothed everything out. But inflation itself is still a mystery. The background radiation does not just answer questions, it forces us to ask bigger ones. Psychologically, signals like this remind us of our need to connect events to meaning. A faint hiss in an antenna seems like nothing. But once we learn it is the oldest signal in existence, it becomes profound, almost spiritual. Humans are meaning-making machines. We take noise and turn it into story. The cosmic microwave background is a perfect example of that instinct, proof that sometimes the most important messages come disguised as static. And there is another layer. This signal is not fleeting like fast radio bursts or rare like gamma-ray bursts. It is constant. It is everywhere. You do not have to wait for it. You do not have to chase it. The afterglow of creation is bathing Earth at every moment, washing over every mountain and city, flowing through every empty patch of sky. It is the one signal we can never escape, because it is written into the very fabric of the universe. So when astronomers say they are listening to the cosmic microwave background, they are not exaggerating. They are literally tuning into the sound of the beginning of time. A faint, relentless hum that has been traveling across the cosmos for billions of years, carrying within it the first clues of why anything exists at all. And maybe that is the most haunting part. In a universe filled with mysterious signals, from pulsars to fast radio bursts to gamma ray alarms, this one is different. It is not a warning. It is not a puzzle waiting to be solved. It is a memory, a fossil of light, a message from a time before there were stars or planets or life. It does not tell us what is coming. It tells us where we came from. And in its faint whisper, the universe confesses its origin story, leaving us to wonder how much more of its past is still hidden in the static. Gravitational waves ripples in spacetime. In September of 2015, a pair of detectors buried in the ground in Louisiana and Washington both twitched almost at the same time. The signal was tiny, lasting less than a second, and the change it caused in the detectors was smaller than the width of a proton. Yet that faint ripple confirmed something Albert Einstein had predicted a century earlier. For the first time, humanity had heard the universe shake. These were gravitational waves, ripples in spacetime itself. Not light, not radiation, not particles, but literal distortions of the fabric of reality racing across the cosmos. The first detection came from two black holes spiraling into each other, colliding with such violence that the energy released in that instant was greater than the light of every star in the observable universe combined. And we felt it here, on Earth, as a tiny tremor in space-time. The idea sounds impossible. How can space, something we usually think of as empty, ripple like water? But general relativity tells us space and time are woven together into a fabric. When something massive accelerates, like black holes or neutron stars colliding, that fabric stretches and squeezes, sending waves outward. Imagine tossing a rock into a pond, except the pond is the universe itself. Those waves keep traveling, and if your instruments are sensitive enough, you can catch them as they pass by. The shock of detecting gravitational waves was not just about proving Einstein right. It was about unlocking an entirely new way of observing the universe. Until then, astronomy relied on light, visible light, radio waves, X-rays. But light can be blocked, scattered, or absorbed. Gravitational waves are different. They travel almost unhindered across billions of light years. They carry information straight from places light cannot escape, like the heart of a black hole collision. For the first time, we were not just seeing the universe, we were listening to it. And what we heard was haunting. The first signal, dubbed GW in 50901 tune, sounded like a faint chirp when converted into audio. Two black holes, each about 30 times the mass of the Sun, spiraled closer and closer until they merged. The frequency of the waves increased as they got nearer, rising in pitch until they collided and rang out in a final echo, a cosmic death cry recorded by instruments here on Earth. That sound was not music. It was physics. It was gravity itself moving through us. But here is where the human mind struggles. We are wired to notice the dramatic, bright flashes, sudden bursts, loud explosions. Gravitational waves are almost silent. They pass through Earth constantly, stretching and squeezing everything without us even noticing. The only reason we can detect them now is because of engineering so precise it borders on the unbelievable. LIGO, the Laser Interferometer Gravitational Wave Observatory, uses lasers to measure distances in tunnels 4 kilometers long, detecting changes smaller than a fraction of a proton. That level of precision is not just science, it feels like magic. And yet, this magic has already rewritten our understanding of the cosmos. gravitational waves have confirmed that black hole mergers are real. They have revealed collisions between neutron stars, producing both gravitational ripples and bursts of light, a cosmic double event that prove these crashes forge heavy elements like gold and platinum. Suddenly, the universe is not just something we look at. It is something we feel shaking beneath our feet. Psychologically, signals like this hit us differently. Light feels familiar. We see it every day. Gravitational waves remind us that reality itself is dynamic, that the stage we live on is not solid but flexible. It unsettles the illusion of stability. We think of space as a silent backdrop. Gravitational waves show us the backdrop is alive, vibrating with the echoes of ancient collisions. It is like realizing the ground beneath you is not still, but quivering with the footsteps of giants you cannot see. What makes them even more profound is their time travel quality. The waves we detect today may have been generated billions of years ago, when life on Earth was microscopic or did not exist at all. They carry the memory of events long past, arriving here as fresh disturbances in space-time. In a sense, every gravitational wave is a delayed message, a postcard from a violent event that has already faded into history. And this is only the beginning. The first detection was just one event. Since then, dozens more have been recorded: black hole collisions, neutron star mergers, even possible hints of exotic objects we do not fully understand. As detectors become more sensitive, we will capture thousands, maybe millions of these ripples. Each one is a new story, a new signal carved into spacetime. So when scientists talk about gravitational waves as ripples in spacetime, it is not just technical jargon. It is literal truth. The universe is constantly vibrating with events so powerful they shake reality itself. And thanks to a century of theory and a few decades of painstaking engineering, we are finally able to listen. These signals are not flashes of light, not bursts of radiation, but the silent music of gravity. A soundtrack the universe has been playing since its beginning, only now revealed to us in the faintest of whispers. Mysterious low-frequency signals from space. Astronomers sometimes describe space as a symphony, but most of us only ever hear the loudest instruments. The bright flashes, the quick bursts, the dramatic explosions. Hidden beneath all of that are the low notes, signals so stretched out and subtle that you need the biggest telescopes and the longest patience to even notice them. These are the mysterious low-frequency signals, and they might be the most important because they carry information about the universe on scales almost too big to comprehend. Low-frequency radio waves have wavelengths measured in meters or even kilometers. That makes them hard to detect from Earth because our atmosphere blocks most of them, and human technology often drowns them out with interference. Yet when we do catch them, they point us toward phenomena that can't be studied any other way. Think of them as the deep rumble of the cosmos, a background vibration that reveals what the universe is doing over billions of years. One of the most intriguing recent findings came from an international project called NanoGrav. Scientists were not listening with one telescope, but with dozens of pulsars scattered across our galaxy. These pulsars act like metronomes, sending out pulses of radio waves at regular intervals. If something disturbs spacetime on a massive scale, the timing of those pulses shifts ever so slightly. After years of listening, researchers noticed a common pattern, a kind of cosmic bass note stretching across the data. The explanation: a possible background of low-frequency gravitational waves, ripples in spacetime caused by supermassive black holes orbiting each other in distant galaxies. If that turns out to be true, it means we are detecting the slow dance of giants, black holes millions or billions of times heavier than the Sun spiraling together over cosmic timescales. These signals are so drawn out they do not chirp like the high-frequency waves from smaller black hole mergers. Instead, they hum across the universe, taking decades or centuries to complete a single cycle. They are not alarms. They are whispers that never stop. And here is where it gets really strange. Low-frequency signals might also come from phenomena we have not even defined yet. Some theories suggest they could carry imprints of cosmic strings, hypothetical cracks in spacetime left over from the earliest moments after the Big Bang. If such strings exist, their vibrations could leave a telltale signature in the low-frequency range. Others speculate about exotic physics, remnants of processes that happened when the universe was only fractions of a second old. In other words, tuning into these signals could let us eavesdrop on the dawn of time itself. The challenge is that humans are not wired to think on these scales. Our senses are tuned for immediate changes. A flash of light, a loud sound, something that happens now. Low-frequency cosmic signals move on timelines that dwarf human life. Some cycles last longer than civilizations. It requires a kind of patience that feels almost unnatural. Scientists dedicate decades to watching the same pulsars, waiting for shifts that might only become clear when enough time has passed. It is a reminder that the universe does not care about our schedules. Its messages come in its own time, not ours, and this patience plays directly into psychology. When people hear about repeating signals or strange hums from space, curiosity kicks in. We want a quick answer. Is it aliens? Is it a message? Is it a warning? But low-frequency signals do not give us that satisfaction. They are slow puzzles. They demand we let go of instant gratification and learn to value the long game. That is uncomfortable, but it is also deeply human. We are storytellers, and these signals are chapters written so slowly we may never see the full plot unfold. Yet we cannot stop reading. The beauty is that even though the signals are subtle, they are powerful. They can reveal the growth of galaxies, the behavior of supermassive black holes, even the structure of spacetime itself. In fact, some astronomers believe low-frequency observations may become the key to answering the biggest questions of all: how the universe evolved, how it is still changing, and whether there are new laws of physics waiting to be uncovered. And here's something humbling. Right now, Earth is bathed in these low-frequency signals. They are everywhere, washing over us, stretching across galaxies, traveling through the void for billions of years before brushing against our planet. We do not feel them. We do not see them. But with enough patience and the right instruments, we can hear the universe humming its deepest notes. So when you think about cosmic signals, do not only picture bright flashes or explosive bursts. Remember the low rumbles, the quiet vibrations that carry the weight of entire galaxies. They may not grab our attention like lightning in the sky, but they are just as real, just as vital. They are the slow heartbeat of the universe, a signal that reminds us how much of the cosmic story unfolds in silence and patience, waiting for us to learn how to listen. The hunt for technosignatures, a SETI research. In the 1970s, astronomers began to realize something strange about our search for life in the universe. We had spent centuries staring at stars, mapping planets, studying biology, and debating philosophy. But what if the clearest evidence of life would not be a fossil or a footprint, but a signal? Not the kind created by nature, not pulsars, not bursts, not black holes, but the unmistakable trace of technology. That idea gave birth to SETI, the search for extraterrestrial intelligence, and it reframed the question entirely. If someone out there has built machines, could we recognize their signals? The hunt for technosignatures starts with a simple premise: technology leaves scars. Here on Earth, we broadcast radio and television signals that leak into space. We shine powerful radar beams. We generate light pollution so strong it can be seen from orbit. These are byproducts of civilization, unintentional fingerprints of intelligence. If another species exists elsewhere, their technology might also spill into the cosmos, and with the right instruments, we might catch it. The shock of this possibility hit hardest in 1977 with the famous WOW signal. Detected by a radio telescope in Ohio, it was an intense, narrowband radio burst lasting 72 seconds. It looked exactly like the kind of signal SETI researchers had dreamed about. Strong, focused, unlike anything produced by natural sources. To this day, no one has explained it fully. The WOW signal did not repeat, but it proved the search was not science fiction. It was a legitimate experiment with the potential to shake the foundations of human history. And here is where SETI gets tricky. Nature is full of signals that look artificial. Pulsars once fooled scientists into thinking they might be alien lighthouses. Repeating fast radio bursts still spark debates about whether they are astrophysical or technological. Our brains are wired to associate patterns with intention, to see design in order. That makes SETI both exhilarating and maddening. Every unexplained signal feels like a maybe, but most turn out to be physics, not intelligence. Still, the hunt continues, and it is evolving. Early SETI focused mostly on radio waves, because they are efficient for communication and travel easily through space. Today, researchers expand the definition of technosignatures. They look for unusual infrared emissions that might indicate giant structures built around stars, like the hypothetical Dyson sphere. They scan for strange chemical signatures in exoplanet atmospheres that could only come from industrial pollution. They even consider optical pulses, flashes of laser light that could outshine a star for a fraction of a second, like a cosmic Morse code. Why pursue all this when the odds seem so slim? Because the payoff is unmatched. Detecting a technosignature would answer one of humanity's oldest questions: are we alone? Even a single confirmed signal would prove that intelligence is not unique to Earth. And from a psychological perspective, that possibility fuels endless curiosity. Humans are drawn to the unknown, and the thought of someone else sending signals across space scratches a primal itch for connection. But here is the validating truth: SETI is not just about aliens. It is also about sharpening our tools and deepening our understanding of the universe. The same telescopes that scan for technosignatures also detect pulsars, map interstellar gas, and study cosmic magnetic fields. Every false alarm teaches us more about natural astrophysics. The hunt improves our ability to separate the artificial from the natural, and that knowledge is invaluable no matter what we find. And yet, the tease remains irresistible. What if the next unexplained burst is not just a magnetar or a misfiring satellite? What if one day, amidst the static, we detect a repeating narrowband signal, perfectly structured, undeniably artificial? What if someone is out there, sending not just physics but communication? That thought lingers in every SETI lab, in every data set, in every long night of listening. There is also a mirror held up to us in this search. If technosignatures are possible, then we ourselves are already broadcasting ours. For over a century, our radio and television signals have been leaking into space. The earliest transmissions are already over 100 light years away. If anyone is listening, they could know we are here. That fact flips the question back on us. What kind of signature are we leaving behind? What story of humanity is already etched into the stars? The hunt for technosignatures is not a guarantee of discovery. It is a wager that the universe may be more crowded than it looks, that civilizations rise and fall, and leave traces just like stars do. We may search for decades or centuries without an answer. But every time a telescope scans the sky, every time an unexplained signal stirs hope, we are reminded that the possibility is real. So when you hear about SETI, do not dismiss it as science fiction. Think of it as one of the boldest scientific experiments ever attempted. We are not just listening for random noise. We are listening for echoes of intelligence, for signs that thought and technology are not unique to this tiny planet. We are listening for proof that the cosmos itself is a conversation, one we have only just begun to hear. Alien megastructures. The Tabby star debate. Back in 2015, the astronomy world was shaken by a star that just would not behave. Kepler Space Telescope data revealed a sun-like star in the constellation Cygnus that dimmed in a way no one had ever seen before. Not by a little. Not by the 1 or 2% that might suggest a planet passing in front of it, but by up to 20%, sometimes even more. That star became famous as Tabby's star, and its strange flickering launched one of the most fascinating debates in modern astronomy. The first shock was how irregular the dimming was. Planets create predictable patterns. You can mark the calendar and know exactly when a planet will transit its star again. Tabby's star did not play by those rules. It dipped randomly, in different amounts, and sometimes for days or weeks at a time. At first glance, it looked less like planets and more like something enormous and chaotic passing across the star's light. That is where the headline-grabbing idea came in: alien megastructures. If an advanced civilization wanted to harvest energy from its star, it might build a massive array of panels or structures around it, something like the long-theorized Dyson swarm. Such a construction project would cause irregular dimming exactly like what Kepler observed. The possibility was thrilling. For once, astronomers were forced to admit that the data matched something no natural model could easily explain. Of course, science demands caution. Jumping straight to aliens is risky, especially when there are countless exotic but natural explanations waiting to be tested. Researchers suggested clouds of dust, swarms of comets, or debris left from planetary collisions. Each hypothesis explained part of the mystery, but never the whole picture. Dust seemed promising because it could scatter light and create irregular dips. But the color of the dimming did not always fit what dust should do. Comets would require thousands moving in perfect synchrony, which felt unlikely. Planetary debris made sense in some ways, but the timescales didn't line up. What makes this so fascinating is the psychological layer. As humans, we are drawn to the extraordinary. When faced with unexplained data, our minds leap to the most dramatic solution. Alien megastructures grab attention in a way that dust clouds never could. The story spread through headlines, news reports, and online forums because it touched that deep curiosity, the dream that maybe, just maybe, we were not alone. But here's the validating truth: even though the megastructure theory is unlikely, Tabby's star still matters. Its bizarre behavior forced astronomers to sharpen their models, to think creatively about what stars and planetary systems are capable of. It proved that our universe still has surprises waiting, that not every star fits neatly into the categories we have built. Even if aliens are not involved, something strange is happening, and studying it teaches us more about the rules of the cosmos. And then there's the tease that lingers. Every time a new analysis explains part of the mystery, another question pops up. Observations in infrared suggest dust might indeed play a big role, but not all the dips are accounted for. Some dimming seems too sharp, too abrupt, too unusual. No single explanation ties everything together neatly. That means the door to speculation never fully closes. The Tabby star debate also tells us something about ourselves. It shows how quickly we turn data into narrative. A light curve is just a graph, but to us it becomes a story. Maybe aliens are building something. Maybe dust clouds are swirling. Maybe comets are breaking apart. We crave meaning, and in that craving, we reveal as much about our psychology as we do about the star itself. There's also a deeper layer of humility. For most of history, stars seemed timeless, steady, perfect points of light. Tabby's star reminds us they are dynamic, messy, and unpredictable. They can flicker, dim, flare, and confuse us. The universe does not exist to be easily categorized. It resists our attempts to put it in a neat box, and sometimes it leaves us with mysteries that remain unsolved for decades. And maybe that is the real lesson of Tabby's star. Whether the explanation is dust, debris, or something we have not thought of yet, the debate itself is valuable. It shows how science progresses, through questions, through competing ideas, through open acknowledgement of mystery. It shows how quickly a single star can spark global curiosity, igniting conversations not just in labs but in living rooms, classrooms, and online communities around the world. So is Tabby's star hiding an alien megastructure? Almost certainly not. But in chasing that possibility, we discovered something just as important. How much wonder is left in the universe, and how ready we are to believe in extraordinary possibilities when the data leaves room. Tabby's star may not reveal other civilizations, but it does reveal our own hunger to find them, our readiness to listen for signals, even when the cosmos is just flickering naturally. And the truth is, the mystery is not finished. The star is still dimming, still behaving strangely, still refusing to give us a final answer. Maybe in another decade, better instruments will solve the puzzle once and for all. Or maybe it will remain one of those cosmic riddles that never fully closes, forever teasing us with the thought that somewhere out there, someone else might be building structures big enough to cast shadows across the stars. Cosmic static, radio noise from the universe. If you have ever turned an old radio dial and heard that faint crackle of static, you have already brushed against the universe itself. Buried inside that noise, hidden between the buzzes and hisses, is a signal that does not come from your speakers or your house or even Earth. A small slice of that static is ancient radiation from the cosmos, a leftover whisper from the birth of everything. That means when you listen to static, you are literally eavesdropping on the universe. For most of us, static feels like nothing, like empty noise. But for astronomers, it is treasure, because inside those random sounding crackles are patterns, and those patterns tell stories about the universe. Some of the static comes from thunderstorms on Earth. Some comes from our own electronics. But a surprising amount comes from space. The sun, for example, blasts out bursts of radio waves that wash across our planet. Distant planets like Jupiter send out strong radio emissions too, generated by their magnetic fields. Even the Milky Way itself contributes a low hum, produced by charged particles spiraling through vast cosmic magnetic fields. The shock moment came in the 1960s when two scientists, Arno Penzias and Robert Wilson, were trying to reduce noise in a giant radio antenna. No matter what they did, the static would not go away. They thought it might be pigeons nesting in the antenna. They cleaned it. They checked every piece of equipment. Still, the hiss remained. What they had stumbled upon was not interference at all, but the faint afterglow of the Big Bang, the cosmic microwave background. That discovery earned them a Nobel Prize and changed cosmology forever. A random hiss in their data turned out to be the oldest light in the universe. This is why cosmic static matters. It is not just noise. It is layered with meaning. Each piece of it is like a note in a symphony, pointing to different sources, different events, different scales of space and time. The static from pulsars can act like lighthouses, keeping cosmic time. The static from distant quasars shows how galaxies evolve. The static from the microwave background reveals the conditions of the universe only hundreds of thousands of years after its birth. And here is where the story gets even more fascinating. Our brains are wired to dismiss noise. Psychologists call it habituation. When a stimulus repeats without clear meaning, we tune it out. It is why you stop noticing the hum of a refrigerator or the ticking of a clock. But science thrives when we resist that instinct. When we ask what looks like a pointless question. Is this noise really just noise? Time and again, the answer in astronomy has been no. What first seemed like random fuzz often hides the most profound discoveries. The validating truth here is that cosmic static is not just a background annoyance. It is the baseline against which all other signals are measured. Without understanding the noise, we could not detect the rare bursts, the repeating patterns, the strange anomalies that hint at new physics. Static is not the enemy of discovery. It is the canvas discovery is painted on, and the tease that lingers is irresistible. If ancient radiation could be hiding inside a hiss, what else could be waiting inside the static we dismiss? Could there be patterns too subtle for us to recognize today? Signals from civilizations so advanced they disguise themselves as background noise. Some researchers in SETI even consider the possibility that an alien signal might not arrive as a clear beacon, but as something hiding inside the chaos, only detectable with patience, persistence, and technology we have yet to build. This makes every crackle on the radio dial feel a little different. It reminds us that the universe is constantly speaking, even when it sounds like silence. It teaches us that noise is not the opposite of meaning. It is the doorway to it. And it leaves us with a humbling thought. Every time you hear static, you are brushing against cosmic history, touching signals that have crossed billions of years to reach you, wrapped in the disguise of noise. So the next time you dismiss a hiss, a buzz, or a crackle as meaningless, remember that the universe itself once hid its greatest secret inside a stubborn patch of static. It is not always the loudest or clearest signals that matter most. Sometimes it is the faintest whispers, the background murmurs, the noise we nearly ignore that end up telling the deepest truths about who we are, where we came from, and how vast the story of the cosmos really is. Strange X-ray signals from black holes. When you think of black holes, you probably picture darkness, an object so dense that not even light can escape. But here's the twist. Some of the brightest signals in the universe actually come from the edges of black holes. Not in visible light, but in X-rays. And these signals are as strange as they are powerful, carrying secrets about the most extreme environments we can imagine. X-rays are produced gets pulled toward a black hole and forms an accretion disk, a swirling whirlpool of gas and dust heating up as it spins faster and faster. Temperatures soar to millions of degrees. At those levels, atoms are stripped apart and radiation pours out in X-ray wavelengths. That means that even though the black hole itself is invisible, its feeding habits light up the cosmos with violent, pulsing X-ray signals. The first shock to astronomers came in the 1960s, when rockets equipped with X-ray detectors picked up powerful emissions from sources that didn't match anything known at the time. These strange signals eventually led to the discovery of black hole candidates. It was as if the universe had been broadcasting the existence of black holes all along, but we only just built the ears sensitive enough to hear them. And the signals themselves, they don't behave like ordinary light. Some X-ray emissions flicker rapidly, changing in milliseconds. Others pulse with eerie regularity, almost like a heartbeat. This flickering is more than a curiosity. It reflects the extreme physics near the event horizon. Matter whips around so fast that its energy output rises and falls as if in rhythm, producing quasi-periodic oscillations. These oscillations are windows into how gravity twists and stretches time near the very edge of spacetime itself. But there's another layer of strangeness. In some black hole systems, astronomers have detected mysterious flares, sudden outbursts of X-rays that brighten dramatically, then fade just as quickly. What causes them? One possibility is magnetic reconnection, where tangled magnetic field lines snap and release bursts of energy, much like solar flares on the sun, but far more intense. Another possibility is that blobs of hot plasma are being ejected outward at near light speeds, producing X-ray fireworks on cosmic scales. Whatever the mechanism, these flares are a reminder that black holes are not quiet, passive monsters. They are dynamic, unpredictable, and violent. And then comes one of the biggest teases of all. Some researchers believe X-ray signals may hold clues about the structure of spacetime itself. General relativity predicts one thing, but alternative theories of gravity suggest subtle differences in how matter should behave near the event horizon. By studying the timing and spectrum of X-ray emissions, scientists are probing whether black holes truly follow Einstein's rules, or if there are cracks in the theory. If anomalies appear, they could hint at new physics beyond what we know, a deeper layer of reality hidden in the dance of X-ray light. There's also the human side to this story. For decades, black holes were thought of as theoretical curiosities, math scribbles in equations, rather than real cosmic objects. It took strange X-ray signals to convince us they were out there. These signals validated the existence of black holes, not through imagination but through data, through stubborn radiation pouring across space. It's a reminder that nature often reveals its most exotic secrets not in clear, dramatic gestures but in strange, noisy signals that demand we pay attention. And it is not just the massive black holes at the centers of galaxies. Stellar, mass black holes in binary systems also produce remarkable X-ray signals. As they siphon matter from a companion star, they create flickers and flares that tell stories of feeding, outbursts, and chaotic cosmic hunger. Some systems even switch states, like mood swings, shifting from quiet, steady emissions to violent, bursting behavior. The signals are as temperamental as they are informative, a cosmic drama played out in invisible light. Here's the validating part. These X-ray observations are not just exotic curiosities. They help us understand how galaxies grow, how stars die, and how matter behaves under conditions impossible to reproduce on Earth. They give us a laboratory for testing physics at extremes we could never build in any particle accelerator. And in doing so, they remind us how interconnected everything is. Black holes may feel distant and alien, but their signals teach us about the same fundamental forces that shape our own planet. Still, the tease is irresistible. Every time a new telescope with sharper X-ray vision is launched, like NASA's Chandra Observatory or the European Space Agency's XMM Newton, we see signals that don't quite fit our models. Flickers too fast, flares too bright, oscillations too strange. Each one whispers that there's more to learn, that the story is not finished. So the next time you hear the phrase black hole, don't just think of emptiness. Think of a beacon blazing in X-rays, flashing signals from the edge of physics itself. Signals that tell us how gravity bends time, how matter behaves when pushed past its limits, and maybe even whether our deepest theories are right or incomplete. The darkness hides the hole itself, but the light at its edge tells a story more thrilling than anything we could invent. Signals from exoplanets, possible clues of atmospheres. In the past, when people asked if other worlds existed, it was a question of imagination. Today, it is a question of data. Astronomers have confirmed thousands of exoplanets orbiting distant stars. And the most exciting thing is not just that these planets exist, but that some of them give off signals. Faint, delicate clues that hint at what their atmospheres might be made of. These signals are so subtle that they arrive as whispers hidden inside starlight. Yet they may be our best chance of finding out if a world could host life. Here's how it works. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere before reaching us. That atmosphere leaves fingerprints, tiny changes in the spectrum of the starlight. With powerful instruments, we can decode those changes and figure out whether molecules like water vapor, methane, or oxygen are present. This is called transmission spectroscopy, and it has already given us the first glimpses of alien skies. The shock moment came in the early 2000s when scientists detected sodium in the atmosphere of a planet called HD 29458b, a gas giant orbiting close to its star. It was the first time humanity had measured the chemical makeup of a world beyond our solar system. Since then, discoveries have piled up carbon dioxide, water vapor, and even possible hints of clouds and hazes drifting across alien horizons. For the first time, we were not just finding planets, we were characterizing them. And the signals keep getting stranger. Some hot Jupiters, giant planets orbiting scorchingly close to their stars, show signs of atmospheres literally evaporating into space, leaving tails of gas like comets. Others show odd imbalances in molecules that challenge our understanding of planetary chemistry. These findings are not just exotic trivia. They are stepping stones toward something bigger, the search for biosignatures. That's the part that really grips the imagination. If we find signals pointing to oxygen and methane together in the same atmosphere, that combination could suggest biological activity. On Earth, life keeps both gases replenished. Without biology, they would react away. So when astronomers scan exoplanet atmospheres, they are not just cataloging chemistry. They are asking one of the most profound questions of all: could something be alive there? But here's the validating truth. Even without life, these signals matter. They tell us how planets form, how atmospheres evolve, and what the diversity of worlds looks like. They help us test theories about climate, habitability, and the limits of planetary systems. Every spectrum, every faint dip in starlight, expands our understanding of what it means to be a planet. And the tease: we are only just beginning. Right now, most of the signals we detect are from giant planets close to their stars, because those are easier to measure. But with telescopes like the James Webb Space Telescope, and even more powerful observatories coming in the future, we are pushing towards smaller, Earth-sized planets. That is where things get thrilling. Imagine detecting the faint fingerprint of water vapor in the atmosphere of a rocky planet orbiting in its star's habitable zone. That would be a game changer. The first solid evidence that a potentially life-friendly world exists. There's also a psychological twist. Humans are drawn to mirrors. When we look into the sky, what we want most is not just a planet, but a planet that feels like home. A rocky surface, clouds drifting across the sky, maybe oceans reflecting starlight. Exoplanet signals play directly into that longing. They offer hints, glimpses, fragments of possibility. We are not seeing those worlds directly, but the data lets us imagine them in vivid detail, as if we are peeking through a cosmic keyhole. The hunt is not easy. These signals are buried in noise, easily drowned out by the brightness of the parent star or interference from Earth's atmosphere. It takes patience, precision, and creative techniques to pull meaning from the static. But that challenge only makes the discoveries more powerful. Every molecule identified in an exoplanet atmosphere is a victory against the odds, a reminder of how far our reach has extended. And the story is far from finished. Right now, signals are hinting at atmospheres that defy easy explanation. Worlds with scorching winds, planets with exotic clouds of molten iron or glass, atmospheres glowing with chemicals that have no earthly counterpart. Some are inhospitable, even hostile. But others may one day reveal the first convincing evidence that life does not just exist here, but thrives across the galaxy. So when you hear about exoplanet signals, remember that they are more than just data points. They are whispers from distant skies, each one carrying a message about what it means to be a world. Some messages tell us about heat and gas and storms. Others may one day tell us about water, oxygen, or even life itself. We are listening carefully, tuning our instruments, waiting for the moment when a signal arrives that changes everything we thought we knew about our place in the cosmos. The role of giant radio telescopes. There's something awe-inspiring about a dish so massive it looks like it could swallow a football stadium. Giant radio telescopes aren't just tools. They're monuments to curiosity, built to listen to whispers from the cosmos that human ears could never detect. They turn radio waves, invisible ripples of energy, into information about black holes, pulsars, galaxies, and maybe even civilizations. Without them, half the cosmic signals we've talked about would still be invisible to us. Take Arecibo, for example. For decades, it was the crown jewel of radio astronomy, nestled into the hills of Puerto Rico. Its dish was more than 1,000 feet across, a massive ear tuned to the sky. With Arecibo, scientists measured the rotation of distant galaxies, mapped near-Earth asteroids, and even discovered the first binary pulsar, work that would later win a Nobel Prize. It wasn't just listening to space, it was shaping our understanding of gravity itself. But Arecibo wasn't only about physics. It was also about hope. In 1974, scientists used it to beam a message toward a star cluster 25,000 light-years away. That broadcast, known as the Arecibo message, was a bold experiment, a binary portrait of humanity sent into the void. It captured the essence of what giant telescopes represent: tools of science, yes, but also instruments of imagination. The shock came in 2020 when Arecibo collapsed. Years of wear and hurricane damage had weakened its cables until one snapped, then another, and finally the platform crashed into the dish. It was a heartbreaking moment for astronomers around the world. A telescope that had defined generations of discoveries was gone in seconds. The loss felt like losing a voice, as if part of the universe's conversation had gone silent. But the story didn't end there. In China, engineers built FAST, the 500-meter aperture spherical telescope. Bigger than Arecibo by a wide margin, it is now the largest single-dish radio telescope on Earth. FAST-T has already detected hundreds of new pulsars, scanning deeper and wider than anything before it. It has the sensitivity to search for faint signals, including potential technosignatures, with a precision that makes it the most powerful ear humanity has ever raised to the sky. And then there's MeerKAT in South Africa, which takes a different approach. Instead of one giant dish, it uses an array of 64 smaller ones, spread out like a network. Together, they create images with astonishing detail, resolving structures in radio galaxies and mapping magnetic fields across interstellar space. MeerKAT is also a preview of what's coming. The Square Kilometer Array, the most ambitious radio telescope project ever attempted, designed to stretch across continents and multiply our sensitivity to cosmic signals beyond anything we've ever achieved. So what role do these giants really play? They are the translators between the silent universe and our human understanding. Radio waves can travel vast distances without being absorbed, carrying information about things we could never see in visible light. Pulsars ticking like clocks, gas clouds forming new stars, black holes flaring at their edges, the faint background hiss left over from the Big Bang. These telescopes let us tune into frequencies that expand our vision of the cosmos. And here's the validating truth: giant telescopes are not just about gathering data. They are about patience, collaboration, and ambition. Building something like FAST or MeerKAT takes decades of planning, thousands of people, and an enormous commitment to curiosity. These machines reflect our willingness to invest in questions that may not have immediate answers, to create instruments not just for today but for future generations. Of course, the tease lingers in every observation. Every time a telescope records a new pulse, a new burst, a new unexplained signal, the possibility of the extraordinary hangs in the air. Could it be a magnetar, a quasar, or something no one has thought of yet? Could it even be a signal from intelligence beyond Earth? SETI researchers certainly hope so, and FAST-T has already dedicated time to searching for such possibilities. The dream is alive every time the dish is turned toward the sky, but perhaps the most powerful thing these telescopes remind us of is scale. Standing beneath Arecibo when it was still alive, or visiting the valley where FAST sits, you couldn't help but feel small in the best way possible. These machines dwarf us, yet they exist only because we built them. They reflect our hunger to reach beyond ourselves, to listen more carefully, to know more deeply. They are proof that when humans pool imagination and engineering, we can build ears large enough to hear the universe breathe. So whether it's Arecibo's legacy, FAST-T's present power, or MeerKAT's detailed vision of the sky, giant radio telescopes are not just machines. They are bridges between silence and discovery. They remind us that the universe is speaking all the time, in signals too vast, too faint, or too ancient for us to detect without help. And they remind us that as long as we keep listening, we may one day hear something that changes the story of humanity forever. The search for extraterrestrial intelligence, past and present. If you trace the dream of finding other intelligent beings in the universe, you discover it's not just a modern obsession. It's one of the oldest human fascinations. Ancient civilizations looked to the stars and wondered who else might be out there. But it was only in the past century that the question shifted from myth and philosophy into science. The search for extraterrestrial intelligence, or SETI, became a real endeavor, grounded in data, telescopes, and technology. And its history is just as fascinating as its future. The shock moment came in 1960 when an astronomer named Frank Drake pointed a radio telescope at two nearby stars. The project was called OSMA, and it was the very first deliberate scientific attempt to listen for alien signals. Drake didn't find extraterrestrials that day, but he ignited a movement. His experiment said, "In effect, this is no longer a fantasy. This is a question science can ask." In the years that followed, SETI grew from a fringe idea into a global pursuit. Radio telescopes around the world joined the effort, scanning the sky for narrowband signals, the kind nature almost never produces but technology might. In 1974, Drake and others used the Arecibo telescope to send a message of our own, a binary broadcast aimed at a star cluster 25,000 light-years away. That moment captured the dual nature of SETI, not just listening but also daring to speak. And then came the mystery that still haunts as history, the WOW signal of 1977. A sudden, powerful burst of radio energy detected by an Ohio telescope that looked exactly like the kind of signal SETI researchers were hoping for. It lasted 72 seconds, then vanished. Never repeated, never explained. To this day, it's the most tantalizing, maybe in the search for intelligence. It proved the experiment was worthwhile, even if the answer wasn't clear. But SETI's past is also filled with challenges. Governments that once funded the work often pulled back, seeing it as too speculative. In the 1990s, the U.S. Congress canceled NASA's major SETI program, leaving researchers scrambling to continue with private support. And yet, the search endured, fueled by the persistence of scientists and the curiosity of the public. Here's the validating truth. Even when SETI doesn't find aliens, it produces value. The same instruments that search for technosignatures also detect pulsars, map interstellar gas, and discover strange cosmic phenomena like fast radio bursts. The discipline sharpens our ability to separate natural from artificial, to sift order from noise. It makes astronomy more precise, and that's worthwhile no matter what the outcome is. Now, in the present, SETI is undergoing a renaissance. Powerful new telescopes like FAST-T in China and MeerKAT in South Africa are dedicating time to the search. Breakthrough Listen, a privately funded initiative backed by billionaire Yuri Milner, has invested hundreds of millions of dollars into scanning the skies with unprecedented sensitivity. They're targeting millions of stars, entire swaths of the Milky Way, and even nearby galaxies. The scale dwarfs anything SETI attempted in the past. And here's the tease that drives the modern search: we now know exoplanets are everywhere. Thousands confirmed. Billions likely in the Milky Way alone. Many inhabitable zones where liquid water could exist. For SETI researchers, that changes everything. Instead of scanning blindly, they can focus on worlds that might actually support life. The odds feel less like a shot in the dark and more like a problem of patience and persistence. Technology has also transformed the game. Artificial intelligence now helps sift through mountains of data, flagging unusual patterns humans might miss. Optical SETI searches for laser flashes that could outshine stars for fractions of a second. Some researchers even propose looking for artifacts, strange heat signatures, unusual chemical pollutants in exoplanet atmospheres, or massive structures around stars. The definition of technosignatures has expanded beyond just radio. Yet, for all this progress, the emotional core of SETI hasn't changed. It's still about listening, waiting, wondering if someone else is out there broadcasting into the void. It's about that moment of possibility, the thought that any unexplained signal could be the one that rewrites history. And it's about humility, too, the recognition that if intelligence exists elsewhere, it might be far older, far more advanced, and far stranger than anything we expect. So when you think of the search for extraterrestrial intelligence, remember it's not just about the past or the present. It's a continuum. From Frank Drake's first experiment, to the WOW signal, to today's massive projects scanning billions of frequencies, the goal has always been the same: to turn an ancient human longing into a scientific question. And as long as we keep listening, the possibility remains alive that one day, in the middle of all the static, we'll hear something that proves we're not alone. Misidentified Earth-based interference, Perseus signals, Wi-Fi, radar. Not every mysterious signal that comes from the sky is actually from the stars. Sometimes, what looks like a cosmic whisper turns out to be a very human shout. Earth is full of radio noise, from Wi-Fi to radar to satellites, and when our instruments pick it up, it can fool even the most experienced astronomers. These misidentified signals are a reminder that listening to the universe is not as simple as pointing a telescope and waiting. Take the Perseus signals, for example. For years, astronomers detected strange radio bursts in a frequency range they did not expect, bursts that seemed almost patterned, almost artificial. At first, the scientific community buzzed with excitement. Could this be a technosignature, a real trace of intelligence somewhere out there? But as investigations continued, the mystery unraveled. The signals were traced back to reflections from Earth-based radar systems, bouncing off the ionosphere and back into the telescope. A cosmic mystery turned out to be a mirror of our own technology. That story is not unique. Every modern telescope is surrounded by a forest of human-made signals. Wi-Fi, cell phone networks, satellites, airplane communications, all of these produce radio waves that can leak into observations. In fact, observatories go to extraordinary lengths to minimize interference. They are often built in remote valleys or deserts, shielded from cities, and even restricted by legal radio, quiet zones. And yet, some signals still slip through, making scientists double-check their work. The shock of misidentification is not just professional embarrassment. It also highlights how easy it is to see patterns where none exist. Our brains are wired to detect intention, to notice rhythm, repetition, and structure. That makes us excellent at finding meaning, but it also makes us vulnerable to false positives. A radar pulse timed just right can mimic a repeating cosmic signal. A satellite transmission bouncing off the atmosphere can appear to originate from a distant star. The cosmos becomes a hall of mirrors, reflecting our own technology back at us. One famous example occurred in the early days of radio astronomy, when pulsar-like signals turned out to be reflections from military radar systems. For a while, researchers thought they had discovered something revolutionary. Only after painstaking correlation with Earth-based transmissions did they realize the signals were terrestrial. These false leads are frustrating, but they also sharpen scientific rigor. They teach us to question every anomaly, to test every hypothesis, and to distinguish the truly extraterrestrial from the mundane. And yet, there is something validating about these mistakes. They are proof that our instruments are working, sensitive enough to detect tiny signals across vast distances. If they pick up a ping from Wi-Fi, they are capable of picking up a ping from space. Misidentifications are not failures. They are milestones along the way, reminders that progress often comes wrapped in false starts. The tease in this story is irresistible. Every misidentified signal leaves a lingering question: what if it had been real? Each time astronomers rule out Earth-based interference, they do so against a backdrop of hope. They know that somewhere, amidst billions of stars, a genuine anomaly might one day appear. The Perseus signals, the rogue radar reflections, the Wi-Fi bursts, they are warnings and training exercises from the universe, preparing us for the moment we finally detect a true cosmic message. It also forces humility. Humanity is loud. We generate enough radio energy to mask subtle phenomena from instruments on Earth. Our cities, our radar, our satellites. All of it creates a background hum that complicates the search for signals from other worlds. Recognizing our own interference is essential, because without that step, we could mistake ourselves for aliens. And yet, misidentified signals do more than frustrate scientists. They spark imagination. Even when the source turns out to be radar or Wi-Fi, the initial thrill reminds us why we search. It is a glimpse of what discovery feels like, a rehearsal for the moment we finally intercept something genuinely extraordinary. Every false alarm is a story, a teaching moment, and a proof of the vastness of both human ingenuity and cosmic silence. The lesson is clear: listening to the universe requires patience, skepticism, and extraordinary precision. Signals must be confirmed across multiple instruments, cross-referenced with databases of human activity, and examined for natural explanations before any hint of aliens is considered. But that doesn't make the search less exciting. In fact, knowing that every signal might have a mundane source makes the rare, unexplained burst even more tantalizing. So, when astronomers report a strange signal, it is worth remembering that sometimes it is just Wi-Fi, a radar pulse, or a satellite. But sometimes those misidentified signals prepare us. They train our ears, calibrate our instruments, and remind us that the universe is full of whispers. Some of them deceptive, some of them profound, and some of them waiting for the first human to recognize them as truly otherworldly. The Enigma of Lorimer bursts. In 2007, astronomers stumbled upon something that would shake the study of cosmic signals, a pulse so brief, so intense, that it seemed to come from nowhere and vanish in the blink of an eye. It lasted only a few milliseconds, but it carried more energy than the sun emits in days. This discovery, now called the Lorimer burst, was the first glimpse of a phenomenon that would later be known as fast radio bursts, or FRBs, and the thing that made it truly mind-bending was that no one could explain it. The shock came immediately. How could a signal so powerful come from such a distant source? The Lorimer burst was traced to a galaxy billions of light years away, meaning it had traveled an unimaginable distance across the cosmos. By the time it reached Earth, it had survived countless obstacles, interstellar gas, magnetic fields, and the background hum of the universe. And yet, it arrived perfectly intact, a single, tiny spike in our instruments. The universe had sent a message, and we barely had time to register it. That first pulse opened a floodgate of questions. What could produce such an energetic burst in such a short time? neutron stars, colliding black holes, magnetars. Some scientists even speculated about extraterrestrial technology. The sheer brevity and power of the Lorimer burst forced astronomers to reconsider everything they thought they knew about high-energy phenomena. For years, it was the lone example, a cosmic ghost that appeared once and then disappeared. And here is where the validating part comes in. Even though it was a single event, the Lorimer burst proved that the universe still holds surprises we cannot predict. Every detection since then, dozens and now hundreds of FRBs, can trace its origin to that first observation. The Lorimer burst acted as a Rosetta Stone, telling astronomers there is a category of cosmic events we had never noticed because they are so fleeting, so rare, so easy to miss. Without it, we might still be blind to this cosmic orchestra. The tease is relentless. Some FRBs repeat, while others seem to occur only once. Some have predictable patterns, almost like a heartbeat, while others are random. The Lorimer burst itself has never repeated, which makes it a tantalizing puzzle. Was it a one-time catastrophic event, or did it simply repeat on a timescale we haven't observed yet? Each new FRB detection adds context, but none fully explains the original pulse. The mystery remains, hanging over radio astronomy like a shadow. Part of what makes Lorimer bursts so fascinating is how they challenge our perception of scale. These signals carry information from billions of light years away, but they arrive in milliseconds. That contrast, immense distance compressed into an instant, is almost impossible for the human mind to grasp. It forces scientists to think in extremes, energy densities, magnetic fields, and cosmic distances that dwarf anything we experience on Earth. And yet, it's measurable, tangible, and real. There's also a human dimension to the discovery. The burst is named after Duncan Lorimer, the astronomer who first identified it while sifting through archival data from a survey of the sky. For years, the signal had been hidden in the noise, overlooked and ignored. It took patience, meticulous analysis, and a willingness to question assumptions to find it. That story is a reminder that cosmic discoveries are often waiting quietly in the data, not in flashy, obvious flashes. The universe is patient, and so must we be. Another twist: Lorimer bursts may help us map the universe itself. As radio waves travel across space, they are dispersed by the intergalactic medium. The timing and frequency shift of these bursts can tell astronomers how much matter they passed through. In effect, each burst becomes a probe, giving us a three-dimensional map of otherwise invisible gas and plasma stretching across billions of light years. What began as a mystery signal now has the potential to illuminate the structure of the cosmos itself. And yet, despite everything we have learned, the enigma of the Lorimer burst endures. No model explains all the properties perfectly. Every new theory, whether magnetars, neutron star collisions, or exotic physics, answers some questions but raises others. The burst is a reminder that the universe is bigger and stranger than we often allow ourselves to imagine. So, when astronomers scan the skies and detect a millisecond flash, they remember the Lorimer burst. It is both a warning and a promise the universe can surprise us in ways we cannot predict, and hidden in a single instant of radio light may lie information that transforms everything we know about reality. That tiny pulse from 2007 continues to echo across the field of astronomy, urging us to look closer, listen longer, and never assume the cosmos has given up all its secrets. Signals from the galactic center, the center of our galaxy, is not a quiet place. Far from the calm star fields we see in the night sky, The galactic center is a maelstrom of energy, gravity, and motion. It is home to a supermassive black hole, countless stars packed densely together, and clouds of gas swirling in chaotic patterns. For astronomers listening in radio, X-ray, and gamma-ray wavelengths, it is like tuning into the loudest, most complex orchestra in the universe, filled with signals that are sometimes beautiful, sometimes baffling, and sometimes completely unexpected. The shock hits immediately when you consider the extremes. Sagittarius A star, the supermassive black hole at the heart of the Milky Way, contains 4 million times the mass of our Sun. Despite its enormous gravity, it is surprisingly quiet in some wavelengths, but bursts of radio and X-ray emissions occasionally flare up, hinting at matter being shredded and accelerated near its event horizon. Each flare is a fleeting signal, a heartbeat from the gravitational giant lurking thousands of light years away. And then there are the pulsars, spinning neutron stars that emit precise, lighthouse-like beams of radiation. Near the galactic center, pulsars are incredibly hard to detect because the dense clouds of gas scatter their signals. Yet when astronomers do manage to pick them up, they serve as cosmic clocks, timing the movements of matter in this extreme environment. Some signals even seem to arrive irregularly, suggesting that the galactic center is a playground for physics operating at its limits, where strong gravity, magnetic fields, and high-energy particles collide in ways we can barely imagine. The validating truth is that signals from the galactic center teach us not just about black holes or pulsars, but about the galaxy itself. By analyzing the timing, frequency, and intensity of these emissions, scientists can infer the distribution of mass, the structure of magnetic fields, and the behavior of interstellar plasma. It is a laboratory for extreme physics, one that we could never replicate on Earth. Every pulse, every flare, every burst carries a piece of a story that has been unfolding for billions of years. But the tease is relentless. Among the many signals detected are mysterious X-ray and gamma-ray bursts whose origins are still debated. Some may come from magnetars, highly magnetized neutron stars, or from collisions of compact objects. Others are still unexplained, tantalizing hints that the galactic center may harbor phenomena we do not yet understand. For SETI researchers, this makes the region doubly interesting. It is dense, energetic, and complex, a place where unusual signals could plausibly hide within the natural chaos. Human ingenuity also plays a part in how we detect these signals. Observatories like the Chandra X-ray Observatory, the Very Large Array, and ALMA use sophisticated arrays and imaging techniques to separate overlapping sources and filter out interference. The galactic center is crowded, noisy, and dynamic. Detecting a single signal is like hearing a single voice in a stadium full of shouting fans. Yet the rewards are extraordinary. Each detection provides insights into how galaxies evolve, how black holes interact with their environment, and how high-energy physics behaves on massive scales. There is a psychological layer to these discoveries as well. The galactic center is both mysterious and familiar. It is our galaxy, home to our sun and our solar system, yet we are observing it from tens of thousands of light years away. Signals arriving from this region connect us to something much larger than ourselves. They remind us that the universe is active, energetic, and sometimes violent, but also intelligible if we have the tools and patience to listen carefully. And perhaps the most exciting aspect is what remains undiscovered. With each improvement in telescope sensitivity and resolution, new signals appear. Radio bursts that might hint at exotic astrophysics, flares that defy timing models, unexplained gamma ray glows that refuse classification. The galactic center is a treasure trove of data, and with instruments like the upcoming Square Kilometer Array and next-generation space observatories, the clarity of these signals will only improve. So when you think of the heart of the Milky Way, do not picture it as quiet or distant. Imagine a place alive with energy, sending complex signals across the galaxy. Each pulse, flare, and burst is a story waiting to be deciphered. Some signals are understood, some are natural curiosities, and some may hold secrets that challenge our understanding of physics itself. The galactic center reminds us that even in the vast darkness of space, there is a rhythm, a pattern, a signal, and if we listen carefully, we may learn more about the universe and our place within it than we ever thought possible. The mystery of Perseus cluster radio emissions. Some of the most intriguing signals in the universe don't come from a single star or galaxy, but from vast clusters of galaxies interacting on cosmic scales. The Perseus cluster, one of the nearest massive galaxy clusters, is a perfect example. It's a sprawling cosmic city, with hundreds of galaxies bound together by gravity, immersed in a sea of hot plasma, and threaded with magnetic fields. And within this environment, radio astronomers have detected emissions that are both strange and mesmerizing, signaling processes that are as powerful as they are mysterious. The shock hits immediately when you realize the scale. The Perseus cluster stretches millions of light years across. Its central galaxy, NGC 1275, hosts a supermassive black hole actively feeding on surrounding gas. As it consumes matter, it launches jets of high-energy particles, which in turn generate enormous radio bubbles that rise through the cluster like cosmic blimps. These bubbles are visible in radio wavelengths, and their scale is breathtaking. They dwarf entire galaxies, stretching hundreds of thousands of light years. Signals from these regions tell us that energy in the universe is not subtle. It moves, flows, and reshapes entire clusters. And then there's the mystery. Some of the radio emissions from the Perseus cluster show patterns and features that don't fit neatly into known models. Observations reveal ripples, waves, and filamentary structures in the plasma that suggest turbulence, shock waves, or even interactions with previously unseen magnetic phenomena. The cluster is not just quiet plasma. It is a boiling, vibrating environment where energy moves in ways we are only beginning to understand. The validating part is that these emissions are not random noise. They encode real physics. By studying the strength, frequency, and polarization of the radio waves, astronomers can infer the density of the plasma, the structure of magnetic fields, and even the history of black hole activity in the central galaxy. Each new observation is like peeling back a layer of the cluster's biography, telling us how these cosmic giants evolve over billions of years. But the tease is relentless. Some radio features in the Perseus cluster seem almost alien in their geometry. Enormous arcs and threads of emission that could be related to unknown interactions between the hot plasma and the cosmic magnetic fields. Could there be processes at work that we haven't even theorized yet? Are we glimpsing a new form of energy transport on a massive scale, something that challenges our current understanding of astrophysics? The signals leave us with more questions than answers. There's also the human dimension. Detecting these emissions requires patience, sophisticated instruments, and ingenuity. Arrays like the Very Large Array and LOFAR can map these emissions in stunning detail, revealing structures invisible in other wavelengths. It is a technical triumph to detect something so faint, spread across so many millions of light years, and extract meaningful patterns from it. Each observation is a testament to human curiosity and our drive to understand phenomena far beyond our everyday experience. Another fascinating aspect is the connection between the radio signals and the dynamics of the cluster itself. The jets from NGC 1275 interact with the hot plasma, inflating bubbles, creating ripples, and driving turbulence. These interactions may regulate star formation, heat the intracluster medium, and even influence the evolution of other galaxies in the cluster. In other words, the radio emissions are not just signals, they are evidence of a cosmic ecosystem in motion, a dynamic system where energy is constantly transferred across immense scales. Psychologically, the Perseus cluster challenges our perception of scale and complexity. On Earth, we experience energy and turbulence on a human scale, in storms, rivers, and winds. In the cluster, the same principles operate across millions of light years, at energies and densities that dwarf anything we can create in a lab. Listening to its radio emissions is like trying to interpret a symphony played on a cosmic scale, where each note spans thousands of years of travel time. The mystery deepens with ongoing observations. New radio surveys continue to reveal unexpected structures, waves, and filaments that challenge theoretical models. Some scientists even suggest that dark matter interactions could play a subtle role in shaping the plasma, adding another layer of intrigue. Each detection is both a confirmation of our capabilities and a reminder of how much we have yet to understand. So, when you think of the Perseus cluster, do not picture a static collection of galaxies. Picture a boiling, shifting, and singing system where radio signals ripple across millions of light years, carrying the story of black holes, plasma, and cosmic turbulence. These emissions are more than just data points. They are a window into the forces shaping galaxy clusters, a reminder that the universe operates on scales and energies that are both incomprehensible and awe-inspiring. The mystery of the Perseus cluster radio emissions invites us to listen, interpret, and marvel, knowing that every new observation could rewrite what we think we know about the cosmos. Odd radio circles, ORCs in the sky, and every so often the universe throws astronomers a curveball that no one sees coming. In 2019, during a radio survey of the sky, scientists stumbled on something that didn't fit into any known category. Strange, circular structures glowing faintly in radio wavelengths. Perfect rings, vast and symmetrical, with no obvious explanation. They weren't galaxies. They weren't supernova remnants. They weren't artifacts of the instruments. These were brand new objects, and they quickly earned a name as mysterious as their appearance: odd radio circles, or ORCs. The shock was immediate. Astronomers are used to surprises, but ORCs were unlike anything seen before. Imagine mapping the sky in radio and finding not stars or galaxies, but glowing halos floating in the darkness, each hundreds of thousands of light years across. At first, only a handful were detected. Their rarity made them even more perplexing. What could generate such massive, faint, and perfectly circular signals? The first thought was interference, maybe some quirk of Earth-based radio systems bleeding into the data. But careful checks ruled that out. ORCs appeared consistently in different surveys, using different telescopes across multiple years. They were real. Another idea was that they might be remnants of supernova explosions, but their scale was far too vast. ORCs dwarfed even the largest known remnants, stretching across intergalactic distances. The sheer size eliminated many familiar explanations. Here's the validating truth. ORCs remind us that the universe still has categories of objects we haven't discovered. For all our technology, for all our surveys, we are still explorers bumping into the unknown. These circles of radio light prove that our maps are incomplete. And they show the power of radio astronomy to reveal hidden structures invisible in optical light. Without radio telescopes like ASCOP in Australia and MeerKAT in South Africa, we would never have seen them. The tease is where things get exciting. What causes them? One leading theory is that ORCs are the aftermath of enormous explosions from galaxies, perhaps bursts of energy triggered by supermassive black holes at their centers. If true, then each ORC could be the echo of a galaxy-scale event, a ripple of energy expanding outward across space. Another theory suggests they might be shockwaves from interactions between galaxies, immense collisions sending energy across millions of light years. Still others propose exotic possibilities involving processes we don't yet fully understand in cosmic magnetism or plasma physics. Part of the fascination lies in their shape. Circles are special in nature. They imply symmetry, a central point of origin, and a powerful event that radiated energy equally in all directions. To see such symmetry at such immense scales is both beautiful and unsettling. It hints at order in the chaos, but also at forces far beyond anything we can imagine reproducing. There's also a human element to the discovery. ORCs were first spotted almost by accident. They weren't the target of the surveys, just strange anomalies in the data. It took open-mindedness to recognize them as new objects instead of dismissing them as noise. That's one of the great lessons of astronomy. Some of the biggest discoveries come from paying attention to the unexpected. Psychologically, ORCs play into our curiosity about patterns in the sky. Humans are drawn to circles. We see them in ripples on water, in planetary orbits, in halos around the moon. To find them in the deep sky, glowing in radio light, sparks a deep emotional response. It feels like the universe leaving geometric signatures for us to decipher. The hunt for ORCs is just beginning. Dozens more have been found since 2019, but that is still tiny compared to the billions of galaxies in the universe. Are they rare cosmic events? Or have they been there all along, hidden until our instruments became sensitive enough to detect them? The answer will shape how we interpret the cosmic environment on the largest scales. And the tease continues. If ORCs are tied to galaxy-scale outbursts, they could be new tools for probing how supermassive black holes influence their surroundings. They might map the invisible threads of plasma and magnetic fields that weave through intergalactic space. Or they might point to entirely new physics, a kind of cosmic behavior we haven't even theorized yet. Each ORC is a riddle, and with every new detection, the mystery deepens. So when you hear the phrase odd radio circles, don't picture something small or trivial. Picture vast halos of energy, hundreds of thousands of light, years wide, glowing faintly against the backdrop of the cosmos. Picture astronomers staring at their data in disbelief, realizing they've stumbled upon a phenomenon with no easy explanation. ORCs remind us that discovery is still alive, that the universe still has secrets, and that sometimes the strangest signals are the ones that expand our imagination the most. Unexplained infrared signals from distant galaxy. When astronomers look deep into the universe, they often use infrared light as their guide. Infrared can pierce through dust, revealing structures hidden from optical telescopes, and it can show us galaxies so far away their light has been stretched by the expansion of the universe. But sometimes, When the data comes back, there are signals that don't make sense. Strange, unexplained bursts or excess glows in the infrared, radiating from distant galaxies with no clear source. These signals aren't just oddities. They may be hints of cosmic processes we don't yet understand. The shock of these findings comes from the mismatch between what we expect and what we see. Galaxies should shine in predictable ways. Stars emit light that can be modeled. Dust absorbs and re-radiates in infrared with familiar signatures. Black holes feeding on matter produce characteristic emissions across multiple wavelengths. Yet, some galaxies show excess infrared radiation that doesn't line up with any of these processes. It's as if something is hiding in the data, adding a glow where none should exist. One early surprise came when astronomers studied what's called the cosmic infrared background, the faint glow of accumulated light from countless galaxies. Embedded in this background were fluctuations, patches of brightness that could not be explained by normal populations of galaxies. Were they ancient, hidden galaxies beyond our detection limits? Or was something more exotic contributing to this diffuse infrared signal? The mystery deepened as more sensitive instruments, including the Spitzer Space Telescope and now the James Webb Space Telescope, revealed faint galaxies with unusual spectra that defied expectations. Here's the validating part: even unexplained infrared signals expand our understanding. They remind us that galaxies are not simple structures. They are ecosystems of stars, dust, black holes, and dark matter interacting in complex ways. When the signals don't match our models, it's not a dead end. It's a doorway. Each unexplained glow is a clue that forces scientists to refine their theories of galaxy evolution, star formation, and cosmic history. But the tease is what keeps astronomers coming back. What could cause these anomalies? One possibility is that some of the excess infrared comes from bursts of star formation so intense that they overwhelm the usual signatures, cloaked in thick blankets of dust. Another idea points to hidden black holes, shrouded in material that absorbs visible light, but re-radiates in the infrared. Still others wonder if entirely new processes, perhaps linked to dark matter interactions, could be contributing. And yes, for those with an eye toward technosignatures, the thought lingers. Could advanced civilizations produce excess waste heat detectable in infrared? It's speculative, but it is a possibility that can't be dismissed outright. The psychological impact of these discoveries is subtle but powerful. Infrared is invisible to our eyes, yet it reveals some of the most important truths about the cosmos. To hear that even in this wavelength, with all our modern telescopes and models, the universe still delivers surprises, stirs something deep in us. It's a reminder that no matter how advanced our tools, we are still explorers standing at the edge of the unknown. Technically, these signals are also a triumph. Instruments like JWST can detect incredibly faint infrared light from galaxies billions of light years away, pushing our vision closer to the dawn of the universe. When anomalies appear, it means the instruments are doing their job, catching whispers of phenomena that earlier telescopes missed. Every unexplained signal is proof that we are finally looking deep enough to challenge our assumptions. And there's another layer of intrigue. Many of these unexplained signals come from the very early universe, when the first galaxies were forming. That means they are not just oddities. They may be windows into how the first structures emerged after the Big Bang. Were the first galaxies more chaotic, more extreme than we imagined? Did they produce kinds of light that we don't yet fully understand? The answers are buried in those faint infrared signals, waiting to be uncovered. The mystery continues as new data rolls in. Some anomalies may turn out to have simple explanations: statistical noise, calibration issues, or overlooked dust processes. But others will remain stubborn, pointing to real gaps in our knowledge. And in those gaps lies the possibility of discovery. So, when you hear about unexplained infrared signals from distant galaxies, don't think of them as glitches or curiosities. Think of them as postcards from the edge of time, faint messages carried across billions of years. Each glow is a puzzle piece, telling us that the universe is still stranger and richer than we imagined. Some may reveal hidden black holes. Some may uncover bursts of ancient star formation, and some may point to phenomena we haven't even named yet. They are not just signals. They are invitations to keep asking questions, to keep building better telescopes, and to keep pushing against the boundaries of what we know. The Kepler mission and strange stellar light curves. When NASA launched the Kepler Space Telescope in 2009, the mission had a clear goal to hunt for exoplanets. Its strategy was deceptively simple. Kepler stared at over 150,000 stars, measuring their brightness with incredible precision, looking for tiny dips in light. If a planet passed in front of its star, even for just a few hours, the star would dim ever so slightly. By tracking these light curves, Kepler could reveal worlds hundreds of light years away. But here's where the shock comes in. Not every dip in brightness looked like a planet. Some stars began showing light curves so bizarre, so unpredictable, that astronomers were left scratching their heads. Instead of neat, periodic dimmings that matched a planet's orbit, there were irregular plunges in brightness, sometimes by as much as 20%. No planet, not even a Jupiter-sized one, could block that much light. Something else was happening. The most famous case became known as Tabby's star, after the astronomer Tabby, who led the research. Its light curve looked chaotic. Sometimes it dimmed for days, sometimes for weeks, sometimes in sharp bursts with no pattern. The star seemed to be winking at us in a code no one could crack. Naturally, theories exploded. Could it be dust clouds swirling around the star? A broken-up comet belt drifting through space? Or, as some headlines sensationalized, could it be an alien megastructure slowly eclipsing the star? Here's the validating part. Kepler's strange light curves showed that the universe is full of surprises, even when we think we've built instruments with a single purpose. The telescope wasn't designed to detect mysteries. It was designed to detect planets. But by being so sensitive, it opened a floodgate of unexpected phenomena. We learned that stars can be far more dynamic and complicated than the static points of light we see from Earth. Kepler revealed stellar activity, pulsations, dust disks, and interactions that had gone unnoticed before. The tease, though, lies in how many of these light curves still defy neat explanations. Tabby's star is still debated today. The leading idea is that dust clouds, unevenly distributed, could be blocking the light. But that explanation doesn't satisfy everyone, because the dimming doesn't behave exactly like dust should. Other stars Kepler observed also showed odd fluctuations, raising the possibility that there are whole categories of stellar behavior we haven't cataloged yet. And then there's the psychological impact. When the public first heard about Kepler's strange light curves, the story caught fire because it brushed against one of humanity's deepest questions. What if we're not alone? Even though astronomers lean toward natural explanations, The mere possibility of technosignatures gave the mystery an electric charge. It wasn't just about data anymore. It was about wonder. These tiny variations in light curves connected directly to our imagination, making us feel as if the stars were whispering secrets we weren't quite ready to understand. Kepler's discoveries also highlight something important about science. Sometimes the most important breakthroughs come from side effects. By looking for planets, Kepler stumbled upon whole new puzzles about stars. This is the nature of exploration. When you look closely at the universe, it will always surprise you in ways you didn't plan for. That's not a flaw, that's the point. Technically, interpreting these light curves requires both art and science. Astronomers must separate true signals from noise, account for instrumental quirks, and compare models of planetary transits versus other astrophysical events. Every strange curve becomes a detective story. What could cause a dip this deep? Why is it irregular? Could it be multiple overlapping events? The process is meticulous, but the stakes are high. A single unexplained light curve can challenge entire theories of stellar physics, and the mystery deepens with ongoing research. As telescopes like TESS and now JWST follow up on Kepler's targets, more stars with odd behaviors are being catalogued. Some will turn out to be dust, some will be swarms of comets or debris. But others may remain stubbornly unexplained, continuing to tease us with the possibility of something we haven't yet considered. Each strange curve is a reminder that light itself is a language, and we are still learning the grammar. So when you think of the Kepler mission, don't just think of the thousands of planets it found, though that alone reshaped our understanding of the galaxy. Think also of the enigmas it left behind, the stars whose signals didn't fit any model. These strange light curves are cosmic riddles, proof that even the most carefully designed missions end up uncovering the unexpected. And maybe that's the real lesson. When you search for planets, you might find mysteries even bigger than planets, mysteries that force you to rethink what the universe is capable of showing us. The 19-minute repeating radio signal of 2022. In early 2022, astronomers monitoring the sky with a radio telescope in Western Australia picked up something that made them stop in their tracks. A signal was pulsing, strong and steady, repeating every 19 minutes like clockwork. For 17 months, this object had been sending bursts of energy toward Earth, each one lasting about a minute. Then, as suddenly as it appeared, it faded away. To this day, no one is entirely sure what it was. The shock comes from just how unusual this behavior is. Most cosmic radio sources have rhythms we can explain. Pulsars, for example, spin fast and flash on millisecond or second timescales. Magnetars can flare, but not with such perfect regularity over so many months. A 19-minute cycle is unlike anything in the catalog of known astrophysical objects. It sat in a strange twilight zone between the familiar and the utterly alien. And what made it even stranger was the signal's intensity. It was bright enough that even amateur-level radio telescopes could have detected it if they knew where to look. That kind of strength usually points to a compact, energetic object like a neutron star or a highly magnetized remnant. But the period was all wrong. It did not fit the models. Astronomers were left staring at the data, realizing they were seeing something the universe had not shown us before. Here's the validating part. Discoveries like this prove that the sky is still full of surprises. The fact that an object could pulse steadily every 19 minutes for over a year, and yet remain completely unnoticed until now, is a reminder that our instruments are only beginning to catch up to the universe's complexity. It also highlights the importance of patience. The astronomers who found it weren't chasing headlines. They were combing through data systematically and stumbled onto something extraordinary. The tease, of course, is the mystery of what caused it. One idea is that it was an ultra-long-period magnetar, a kind of neutron star with an extremely strong magnetic field, rotating much more slowly than usual. If true, it would be the first of its kind ever detected. Another possibility is that it was some exotic remnant of a collapsed star, perhaps in a transitional phase we've never observed before. And yes, in the background of these scientific theories, the inevitable question surfaced: could such a repeating, persistent signal be a sign of something artificial? A beacon? A transmission? Most astronomers lean toward natural explanations, but the shape and rhythm of the pulses left just enough room for speculation. The psychological effect of a discovery like this can't be overstated. Humanity has always been attuned to rhythm, from the beat of drums to the ticking of clocks. When we find a rhythm in the sky, especially one so unusual and steady, it resonates with us in a way that feels personal, almost intentional. It's hard not to wonder if someone or something is out there keeping time. Technically, the discovery was made possible by the Murchison Wide Field Array, a low-frequency radio telescope designed to scan wide swaths of the sky. It was not looking for anything like this when the signal appeared. That in itself is fascinating. The telescope caught a phenomenon outside its original purpose. It's a reminder that sometimes the most groundbreaking discoveries arrive when you're not searching for them directly. The timing of the signal also adds another layer of intrigue. For 17 months, it repeated with remarkable consistency. Then silence. If it was a natural object, why stop? Did the star collapse further? Did the magnetic field decay? Or was it simply a transient phase in a life cycle we've never witnessed before? And if you lean into the more speculative side, the question becomes even more unsettling. If it was artificial, why would whoever sent it switch it off? The mystery continues, because the signal hasn't been heard again. Despite follow-up observations with multiple telescopes, the 19-minute beacon has not returned. That absence creates tension. We had a window into something extraordinary, and then the window slammed shut. It feels like being given a single page of a book, only to have the rest locked away. So what do we make of it? The most likely explanation is that it was indeed a rare kind of magnetar, a star that challenges our understanding of how long these objects can spin and still emit powerful radio signals. If true, then it means there may be more of these ultra-long-period objects lurking in the galaxy, waiting to be found. But there's always the chance, however slim, that it was something entirely new, something that forces us to rethink the categories we use to describe the cosmos. The 19-minute signal of 2022 is a perfect example of how the universe teases us. It gives us a taste of the unknown, then takes it away, leaving us with questions that ripple far beyond the original discovery. Was it a dying star in its final act? A new class of cosmic lighthouse? Or a beacon from intelligence beyond Earth? Whatever the answer, it left an indelible mark on astronomy, proving once again that the sky is far from silent. Solar signals bursts from our own star. Most of the time, when we talk about strange signals from the cosmos, we're thinking about distant galaxies, black holes, or mysterious bursts billions of light years away. But one of the most fascinating signal sources is right in our own backyard. The sun, our star, is constantly sending out powerful bursts of energy, radio waves, X-rays, gamma rays. And sometimes those signals are as strange and dramatic as anything we detect from deep space. The shock comes when you realize just how noisy the sun really is. To the naked eye, it looks calm, a glowing disk that rises and sets each day. But in radio wavelengths, it's alive with activity. Solar flares erupt like sudden explosions, releasing as much energy in minutes as billions of nuclear bombs. Coronal mass ejections hurl charged particles across the solar system, producing radio bursts that can sweep past Earth and rattle our magnetic field. At times, the sun even drowns out all other radio signals in the sky, blasting out so much energy that it overwhelms telescopes. It isn't a quiet star. It's more like a cosmic drummer, pounding out rhythms of plasma and light. And then there are the strange details. Some solar radio bursts show patterns that sound almost like whistles or chirps when converted into audio. They drift in frequency as if the sun is playing scales. Others appear as rapid, repeating pulses that last only fractions of a second, but with intensity strong enough to swamp spacecraft receivers. For scientists, these signals are not just curiosities. They are fingerprints of the processes unfolding in the solar atmosphere: magnetic reconnection, plasma waves, and shock fronts racing outward through the corona. Here's the validating part. Solar signals are not only fascinating, they're deeply practical. Studying them helps us understand space weather, the kind of storms that can disrupt satellites, knock out power grids, or even endanger astronauts. When we monitor the sun's radio emissions, we're not just listening to noise. We're gathering real-time warnings about events that could affect life on Earth. In fact, agencies like NASA and NOAA run daily monitoring programs, scanning for unusual solar bursts that could indicate trouble heading our way. But the tease lies in how much we still don't know. Some bursts don't fit standard models. For instance, Type 3 radio bursts, those fast, drifting whistles, are thought to come from beams of electrons shooting through the corona. But the details of how those electrons accelerate so rapidly are still debated. Other mysterious bursts, detected during powerful flares, show fine structures that look almost like coded patterns, too precise to be random turbulence. Are we simply seeing the signature of plasma waves interacting in complex ways? Or are there processes we haven't yet identified in the sun's magnetic heart? There's also the psychological side. We tend to think of the sun as familiar, ordinary, a part of daily life. But when we hear it speaking in radio, chirping and booming across frequencies, it feels alien. It reminds us that the sun is a star, and stars are violent, unpredictable, and powerful. That shift in perspective can be unsettling. The same object that gives us warmth and light is also capable of sending out signals strong enough to knock out communication systems and reshape modern life in an instant. Technically, capturing solar signals requires both speed and precision. Because bursts can rise and fall in milliseconds, radio telescopes need to sample data at incredibly high rates. Instruments like the Solar Dynamics Observatory and ground-based arrays such as LOFAR and the Very Large Array have given us detailed maps of these bursts, showing how they evolve across the solar disk. Each new observation reveals the sun as a dynamic laboratory of plasma physics, one that still has plenty of surprises to offer. And then there's the ultimate tease. We've only observed the sun in detail for a tiny fraction of its life. Over billions of years, how many kinds of signals has it produced? Are there rare, extreme events we haven't yet witnessed. Bursts so powerful they could reshape our understanding of stellar activity. Missions like the Parker Solar Probe, which is flying closer to the Sun than any spacecraft in history, may one day capture signals at the very source, peeling back mysteries that have baffled us for decades. So the next time you think of strange cosmic signals, don't just imagine distant galaxies or exotic black holes. Remember that our own star is constantly sending out messages, broadcasting in a language of plasma and magnetism. Solar signals are proof that the universe's mysteries aren't always far away. Sometimes they're right above us, written in the rhythms of the sun, waiting for us to listen, to learn, and to prepare for whatever bursts may come next. Radio silence zones, why we need quiet skies to listen. If you step outside on a clear night and look up, the stars seem quiet. But in reality, the sky is alive with signals. Pulsars ticking like clocks, galaxies humming faintly in radio waves. Even the afterglow of the Big Bang is whispering across the spectrum. The problem is, here on Earth, we are drowning in our own noise. Cell towers, satellites, Wi-Fi routers, car ignitions, even microwave ovens. All of it creates a fog of interference. To truly hear the universe, astronomers need something that's become increasingly rarer: silence. The shock is that silence doesn't happen naturally anymore. In most places on Earth, the radio spectrum is so crowded that faint cosmic signals are buried under layers of human-made static. Imagine trying to listen for the chirp of a bird in a stadium full of people yelling at once. That's what radio astronomers are up against. Some of the most important discoveries: fast radio bursts, pulsars, subtle emissions from distant galaxies, would have been impossible in a noisy environment. Without protection, the faintest signals risk disappearing altogether, erased before we even know they exist. This is why radio quiet zones exist. These are special areas, sometimes spanning thousands of square kilometers, where radio transmissions are restricted or heavily limited. The most famous in the United States is the National Radio Quiet Zone in West Virginia and Virginia, home to the Green Bank Telescope. In this zone, Wi-Fi is restricted, cell signals are minimized, and even certain electronics are tightly regulated. It sounds extreme, but it's the only way to give astronomers a chance to listen without interference. Here's the validating truth: these zones aren't just about science. They're about preserving the ability to discover. Radio telescopes are some of the most sensitive instruments ever built. They can detect signals 1 billion times fainter than what your phone picks up. But that sensitivity is a double-edged sword. The same telescope that can hear a galaxy 10 billion light years away can also be deafened by a single passing plane's radar or a burst from a nearby cell tower. Without quiet skies, the universe becomes invisible in one of its most important wavelengths. The tease is what we might miss if we don't protect these windows of silence. Some of the strangest signals: fast radio bursts, repeating mysteries, unexplained emissions from clusters of galaxies, all hide at the edge of detectability. If human interference gets louder, those edges blur and vanish. It's possible we could miss the next "wow" signal, the next breakthrough in cosmic understanding, simply because our own devices shouted louder than the cosmos. That thought is both sobering and thrilling. Silence might hold secrets we'll never hear if we don't make room for it. There's also the psychological side. Modern life bombards us with noise. We're used to constant connection, constant transmission. But in these radio quiet zones, there's an enforced calm. Residents often have limited cell service, no broadband in certain areas, and strict rules about electronic devices. For some, it feels like a sacrifice. For others, it's a relief. And for the astronomers, it's a sanctuary. One of the only places on Earth where they can truly open their ears to the cosmos. Technically, the challenge is only growing. With the explosion of satellite constellations, the skies are becoming crowded in ways radio astronomers could barely imagine a few decades ago. Each satellite can flood frequencies with signals that bleed into radio bands astronomers need. Shielding telescopes from that kind of interference is nearly impossible. The only defense is regulation, coordination, and zones of enforced quiet where Earth itself stops shouting long enough to hear the universe's whispers. And yet, here lies the ultimate tease: silence is fragile. Radio quiet zones are constantly under pressure from commercial demands, expanding networks, and the simple desire for connectivity. Maintaining these sanctuaries requires constant negotiation, funding, and public support. The irony is that the discoveries made possible by silence, new exoplanets, gravitational waves, insights into the early universe, often capture global headlines, but the quiet that makes them possible is rarely celebrated. So, the next time you hear about a strange cosmic signal, a repeating burst, an unexplained emission, a whisper from the dawn of time, remember that it didn't just require a powerful telescope. It required silence, a patch of Earth where humanity agreed to lower its own voice, so the universe could be heard. Radio silence zones are not just about quiet skies. They're about protecting the possibility of discovery itself. Because without them, the most profound signals may pass us by, lost forever in the static of our own making. The Drake equation and the probability of alien signals. Back in 1961, a group of scientists gathered in West Virginia to talk about a question that has haunted humanity for centuries: are we alone? To frame the discussion, an astrophysicist named Frank Drake scribbled an equation on the chalkboard. It wasn't meant to solve the mystery outright. It was meant to start the conversation. That simple formula became legendary, and today it's known as the Drake equation, a tool for estimating how many intelligent civilizations might be out there, broadcasting signals into the cosmos. The shock of the Drake equation is how it breaks down a seemingly impossible question into pieces. Instead of asking vaguely whether aliens exist, it asks us to think step by step. How many stars form each year in the galaxy? How many of those stars have planets? How many of those planets are in the habitable zone, where liquid water could exist? Of those, how many actually develop life? And of those, how many evolve into intelligent beings capable of building technology and sending out signals? Finally, how long do such civilizations last before they fade away? When you multiply those factors, you get an estimate, not of certainty, but of possibility. Depending on the numbers you plug in, the answer can swing wildly. Some combinations suggest the galaxy is teeming with civilizations, broadcasting all the time. Others suggest we might be the only ones, a lonely outpost in an otherwise silent universe. That range is both exhilarating and sobering. Here's the validating part: the Drake equation doesn't claim to know the truth. Its power lies in forcing us to confront the unknowns. When Drake wrote it down, many of the factors were pure guesses. Today, thanks to missions like Kepler and TES, we know that planets are common. In fact, there are likely more planets than stars in the galaxy. We also know that a surprising number of those planets lie in habitable zones. So already, parts of the equation have shifted from speculation to evidence. We've moved from ignorance to knowledge, and that's a massive leap forward. But the tease is in the factors we still don't know. How often does life actually emerge once conditions are right? On Earth, life appeared relatively quickly after the planet cooled, which suggests it might not be rare. But intelligence took billions of years to evolve. Does that mean civilizations are incredibly rare, or just slow to appear? And what about the lifespan of a technological society? Do most civilizations burn out quickly through war, climate collapse, or other catastrophes? Or do some endure for millions of years, filling the galaxy with signals we haven't yet detected? This is where the emotional weight of the Drake equation really hits. It reminds us that the answer isn't just about math. It's about perspective. If intelligent civilizations tend to last only a short time, then maybe we're living in a brief window, a lonely echo in a galaxy that has seen countless civilizations rise and fall before us. On the other hand, if civilizations can endure, then we may be surrounded by signals right now, waiting for us to build the tools to hear them. The psychological side is powerful. The Drake equation invites us to imagine where we fit into the story of the universe. It forces us to look at our own civilization and ask, will we last long enough to become part of the galactic conversation? Or will we vanish before we ever send out a meaningful signal? That uncertainty is both terrifying and motivating. Technically, the equation has evolved too. Some scientists propose adding new factors, like the probability of detecting signals or the likelihood of civilizations choosing to remain silent. Others argue that instead of multiplying uncertainties, we should think in terms of ranges and probabilities. But the core idea remains the same: break down the impossible into manageable questions, and suddenly the unknown feels just a little more approachable. And the tease lingers every time we improve our telescopes. Every time we scan a new region of the sky, we chip away at the unknowns. We may never pin down the exact number of civilizations in the galaxy, but we don't need to. Even detecting a single alien signal would answer the deepest part of the question: we are not alone. Until then, the Drake equation sits like an unfinished riddle, reminding us of how much we've learned and how much still waits to be discovered. So when you hear about the Drake equation, don't think of it as just math on a chalkboard. Think of it as a framework for wonder. It is a reminder that the search for alien signals is not just about antennas and data streams. It's about curiosity, humility, and the possibility that somewhere out there, another civilization is asking the same questions about us. How astronomers distinguish signals from noise. When you first hear about strange signals from space, it sounds thrilling, like messages arriving from the cosmos. But here's the truth most people don't realize. The overwhelming majority of what astronomers pick up is noise, static, interference, random bursts from Earth's own technology. Finding a real cosmic signal is like trying to hear a single violin in the middle of a roaring thunderstorm. The art, the science, and the patience all lie in figuring out what's real and what's just junk. The shock is how deceptive noise can be. In 2015, astronomers at the Parkes Observatory in Australia thought they'd found a new mysterious signal. It turned out to be interference from a microwave oven in the staff kitchen. Another time, unusual blips that puzzled scientists for days were traced back to a passing airplane's radar. These false alarms aren't embarrassing. They're inevitable. The universe speaks faintly, while our own machines scream loudly across the same frequencies. Without extreme care, we drown in illusions. But this is where validation comes in. Astronomers don't just shrug and guess. They've built sophisticated systems to sort signal from noise. One of the most important tools is repetition. A true cosmic signal can often be detected again, from the same spot in the sky, at a predictable frequency. Noise, on the other hand, tends to be one-off, scattered, and inconsistent. Another method is triangulation. If two or more telescopes, far apart, detect the same thing at the same time, chances are much higher that it's real. That's why collaborations between observatories are so vital. It's a global form of double checking. Think about how your brain works in a crowded room. You hear a mess of voices, but when your name is called, your attention snaps to it. That's called the cocktail party effect. Astronomers do something similar, training computers to sift through the chaos and highlight patterns that stand out. These patterns might be narrow band signals, the kind nature rarely produces but technology often does. Or they might be bursts at frequencies associated with cosmic events like pulsars or fast radio bursts. By teaching machines to recognize these fingerprints, astronomers can home in on the rare, authentic voices of the universe. The tease is that sometimes the line between signal and noise blurs. There are bursts we still don't fully understand. Take fast radio bursts. At first, many thought they were just interference because they were so brief and strange. But repeated detections from different telescopes confirmed they were real and coming from billions of light years away. Even now, we don't fully know what causes them. In a sense, the most exciting signals often begin their lives disguised as noise. They only become extraordinary once we recognize the pattern hiding within. The psychology of this work is fascinating too. Astronomers have to balance skepticism with curiosity. Too much skepticism, and you might dismiss a real discovery. Too much excitement, and you'll chase microwave ovens and Wi-Fi routers instead of cosmic mysteries. That tension creates a kind of scientific discipline, one that values patience and rigor as much as imagination. The WOW signal of 1977 is a perfect example. It was strong, it was clear, and it still hasn't been explained. But without repetition, it remains an unsolved puzzle, hovering between the categories of signal and noise. Technically, the process is relentless. Data streams pour in at staggering rates. Terabytes every night from large radio telescopes. Computers run algorithms to filter out known sources of interference, like satellites and aircraft. Signals are checked against databases of Earth-based transmissions. Human experts then examine the most promising candidates, looking for consistency, origin, and structure. It's like a giant sieve layer after layer of filtering, until only the rarest grains remain. Most of what's caught turns out to be nothing, but the few that survive can change astronomy forever. And here's the ultimate tease: as technology improves, both sides of the challenge grow. Our telescopes are getting more sensitive, able to detect fainter and fainter whispers from the universe. But at the same time, Earth is getting noisier. More satellites, more transmitters, more interference. The better we get at listening, the more careful we must be in deciding what counts as a true cosmic voice. That means the work of distinguishing signals from noise is never finished. It only gets more demanding, more critical, and more exhilarating. So the next time you hear about a strange burst from the cosmos, remember the invisible battle behind the headline. Somewhere, astronomers worked through mountains of static, discarded countless false alarms, and fought to separate the violin from the thunderstorm. The story of cosmic signals isn't just about discovery, it's about discipline. Because in the end, the greatest mysteries of the universe aren't handed to us clearly. They come wrapped in noise, waiting for us to listen hard enough, long enough, and carefully enough to tell the difference.